ठीक। हम्म। हेलो हेलो चेक। हेलो हेलो।
ओके, वो लिंक मुझे शेयर कर सकते हैं? जी सर। मुझे ईमेल कीजिए।
Hello.
So welcome everyone to the third day of the FSTTCS conference, and it's my great pleasure to introduce and welcome Prasad Raghavendra. He is professor in computer science in Berkeley, and he did his PhD from University of Washington, advised by Venkatesh and Guruswamy, and his work has been very influential in understanding the complexity of various problems, and also developing newer algorithmic techniques. In his doctoral work, he showed a very tight connection between the performance of certain SDP relaxations on constraint satisfaction problems and the unique games conjecture based inapproximability for them, which won the Stock 2008 Best Paper Award. He then further studied these things. He and his co-authors proposed the small set expansion hypothesis, which implies the unique games conjecture. Then on the other side, he also studied more powerful relaxations, the sum of squares hierarchy, SDP relaxations, and their power and limitations. In particular, he and his co-author showed the first super polynomial lower bounds for the semi-definite extension complexity of polytopes for natural optimization problems, which again won the Stock 2015 Best Paper Award. Among other recognitions, he has received the Sloan Fellowship as well as the Michael and Sheila Held Prize. Welcome, Prasad, and today he'll talk about using the SOS hierarchy in newer ways.
Thank you. Thanks for the kind introduction. Thank you to the organizers for inviting me to the conference. I wish I could have spent more time at the conference. Unfortunately, due to personal obligations, I only had to spend less time. So today my talk is titled Measuring Average Case Complexity via Sum of Squares Degree. The talk will meander a bit. Please forgive me for that. It's more of a survey talk. There will be not too much of hard technical content, and it's a short talk. Please stop me if something is not clear. I'm happy to take questions as the talk proceeds. So here's the outline for the talk that I prepared today. So the first part of the talk, I will give a very brief introduction to sum of squares proofs and sum of squares SDPs. This is probably the shortest and most direct introduction to sum of squares that I've ever given, so it's pretty brief. And then after that, I will consider this theme of using sum of squares SDPs to measure average case complexity. And in this theme, I will present three cases. The first one is random 3-sat, for which is actually a success story. The other two are future, ongoing work or future research directions, and I hope I can compel some of you to take up these directions. Okay, so let's start with sum of squares proofs. Here's a brief introduction. So suppose I ask you to solve this system of polynomial inequality. So here, this is one inequality in one variable over the real numbers. And you try to find X that satisfies this for a while, and you can't. And then you probably guess that this system is infeasible. But how do you prove it? So here's a short proof of infeasibility. You notice that this univariate polynomial can be written as 1 plus 1 minus x whole square plus 1 minus x square whole square. Okay. And in particular, this identity tells you that this polynomial is actually 1 plus a sum of squares of polynomials. So given this identity, you can easily check it because you just have to expand it out and see that the coefficients agree on the left and the right hand side. So it's a proof. And it's a proof that this polynomial is greater than or equal to 1 over real numbers, because the sums of squares of polynomials is always non-negative. And therefore, this polynomial is at least 1 plus the sums of squares of polynomials. So it's always at least 1. So it's a proof of infeasibility of this system. So it's natural to wonder, is this an accident? Could we do this all the time? Whenever we have a polynomial which is infeasible, can we prove that it's infeasible by writing it as a sum of squares of polynomials? And good news, for the case of univariate polynomials, it turns out that this is in fact true, that you take any polynomial p of x, which is non-negative, then you can write it as a sum of squares of polynomials. And this is an if and only if. So if p is non-negative, then it can be written as sums of squares of polynomials. And if p is sums of squares of polynomials, then it's of course non-negative. So in other words, this particular proof system of writing the polynomial as a sum of squares of other polynomials is a complete proof system in this context, meaning every polynomial inequality in univariate polynomials that's actually true in one univariate polynomial can be expressed using this proof system, can be shown using this proof system. Okay, that was one polynomial. So suppose we move to multivariate polynomials. So let's say you have 3 polynomials, P1, P2, P3. These are polynomials in X, Y, Z, although my notation seems to suggest they're polynomials in X, just X, Y, Z. And this system of inequalities is infeasible. And how does one prove this thing? Well, again, you could try to use sums of squares of polynomials to derive a contradiction or something that proves that this system is infeasible. So here's an identity. I'm just throwing this identity at you, but it's an identity. So what is happening here? So the first line is the first polynomial times a non-negative number. The second line is the second polynomial times a non-negative number. The third line is the third inequality times a non-negative number, plus a bunch of sums of squares. And this entire sum is equal to -1. So what that means is if all 3 of these inequalities were true, P1 of x, P2 of x, P3 of x, all of them were greater than or equal to 0, then you derive at a contradiction because the right-hand side is non-negative, the left-hand side is -1, right? So this is a proof of infeasibility, right? And it's again based on using sums of squares polynomials. So more generally, if you give me a system of polynomial inequalities, let's say P1 of x, P2 of x, Pm of x greater than or equal to 0, your system of polynomial inequalities, an SOS proof of infeasibility is an identity. It's just an identity of this form. -1 is equal to sums of squares polynomial plus your inequalities times sums of squares polynomials. So -1 is equal to SOS 0 of x, which is sums of square polynomial, which is non-negative. And then sum over I, SOS I of x times Pi of x. Pi of x is greater than or equal to 0, therefore this thing is non-negative. So this identity tells you that these inequalities cannot all be simultaneously true. Okay? And here by a sum of squares polynomial, I mean SOS I of I is actually a sum of squares of polynomials in individual variables. And then the degree of a proof, which is our main measure of the complexity of the proof. The degree of the proof is the maximum degree of any term that appears when you expand it out, right? So when you expand it out, you'll get terms in all the variables of various degrees. You look at the maximum degree of any term that appears in there, and that you call that the degree of the proof. And again, you could wonder, can we always have a sum of squares proof whenever a system is infeasible? And it turns out that that actually, yes. So if you're given any system of polynomial inequalities, pi of x I equal to 1 through m, then the system is infeasible if and only if the P admits a SOS proof of infeasibility. So that's actually very good. So in particular, any statement about multivariate polynomial inequalities that's actually true could be written using a sum of squares proof, could be demonstrated using a sum of squares proof. So that's good, but this theorem does not give you any effective bound on the degree of the proof system. It just says that there exists some finite degree at which there will be a SOS proof of infeasibility. So why does this have to do with algorithms? The reason this has to do with algorithms is that you can actually search for low degree sum of squares proofs efficiently. So in particular, a sequence of works showed that you can search for degree D proofs of infeasibility in time n to the order d. So if d is a constant, in polynomial time, you can find a proof of infeasibility of a polynomial system. I should put a star on this theorem because this is true if you don't take into account the size of the numbers in these proofs, size of the coefficients. And in most natural situations, the size of the coefficients don't blow up. But it's not necessarily true in every situation that searching takes time n to the order d. So if we focus only on not on the coefficient sizes, but on the number of variables, in terms of that, the complexity is really n to the order d. Okay, so what does this give us? So this gives us kind of a hierarchy of algorithms. Because suppose you have a polynomial system P with some set of inequalities, you can reason about this polynomial system by using like this hierarchy of algorithms. So first you could search for a degree 2 proof of infeasibility of the polynomial. Okay, that will take n to the order 1 time. And then you can look for a degree 4 proof of infeasibility of the polynomial system. Or more generally, you can look for a degree D proof of the infeasibility of the polynomial system. And we are guaranteed that if the polynomial system is infeasible, there is some finite degree at which you will actually find a proof of infeasibility. So in a sense, this is a hierarchy of algorithms that take increasingly longer time. In fact, the time grows exponentially with the level of this hierarchy. But it's a very powerful primitive because it lets you reason about polynomial systems. And polynomial systems are everywhere, right? You can pretty much cast lots of optimization problems or search problems as solving polynomial systems. So therefore, it's a very powerful algorithmic primitive if you can just reason about that, if you can find out when they're feasible or not. And I should add that in general, of course, given a system of polynomial inequalities, checking for feasibility is NP complete. So this problem is NP complete, but what this gives you is a hierarchy of algorithms. Okay, so this hierarchy of algorithms is a very, very powerful algorithmic paradigm. Firstly, because as I said, polynomial systems are everywhere. And secondly, also because as an algorithmic technique, I didn't give any details of the algorithm, but if you look into the algorithm, it actually unifies and generalizes two major algorithmic tools, namely spectral methods and linear programming. So, spectral methods and linear programming are two very powerful algorithmic tools. This is kind of unifies and generalizes both of them. Yes. 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 So the question was about what happens on an NP complete system So let's take a 3 sat on n variables and you write it as a polynomial system, and the degree of infeasibility, the degree of sum of squares proof would be n. So the theorem just says that for any fixed polynomial system, there's a finite integer at which there's a sum of squares proof, at finite integer degree at which sum of squares proof. But if the system is of size n, the integer could be n or even larger. Okay, so, and more anecdotally, like if you look at degree 4, degree 2 or 4 or SOS-SDP, it already captures a lot of the very well-known algorithms in classic approximation algorithms like Gomans-Williamson, graph coloring, Loas theta function, Kargam-Motwani-Sudan, Arora-Rao-Wazirani, sparse cut algorithm, max 3-sat, max CSPs, all of these. And if when you go to higher degree SOS-SDPs, it actually turns out that you get lots of new algorithms, which, for problems which we didn't have earlier. For example, there's a bunch of work on robust statistics that use higher degree SOS-SDPs. For example, robust and heavy-tailed mean estimation, robust regression. So you just want to fit hyperplay into a bunch of data points where a lot of it are corrupted. You get algorithms using SOS-SDPs, learning mixture, Gaussian mixture models, max bisection, learning quantum Hamiltonians, and so on and so forth. The list keeps growing every few months. But basically, as it turned out, the higher degree SOS-SDPs actually have led to a lot of interesting algorithms. And in many cases, we don't have another way of getting those algorithms. So, I just, forgive me for, throwing up this list on you, but it's basically, I just wanted to convince you that SOS-SDPs are a fairly powerful algorithmic technique. And in many contexts, they are the most powerful algorithmic technique that we have. Okay, so that brings us to our next theme here. The theme is, the claim is, we can use the SOS-SDP in order to measure the average case complexity of a problem. So given a polynomial system, let us say the SOS degree is the smallest degree at which there is an SOS proof. Okay, you have a polynomial system, you can define SOS degree. So SOS degree is a measure of the complexity of the polynomial system. And the SOS degree, you can see that it's a structural number. Given any polynomial system, there's some number which is at the degree at which there's a sum of squares proof of infeasibility. So it's a structural measure of complexity. So you can actually measure it, you can, in principle. And so the hope is that you can use that as a measure to measure average case complexity and to study this. So let me give you an example. So here's a first example I'll talk about, which is random CSPs. So the most classic one is random 3-sat. So we all know what 3-sat looks like. So 3-sat is you have a bunch of Boolean variables and clauses which look like xi or not xj or xk. And a natural distribution for 3-sat instances is the following. You just have n variables, and the constraints are uniformly random 3-sat clauses on the n variables. So there are 8 n cubed clauses. So you sample m of those clauses independently at random, and that's your 3-sat instance. So since we're studying average case complexity, we have an input which is we not only have an input which is a 3-sat instance, we have a distribution of inputs, and in this case it's the most natural random 3-sat distribution. Okay, of course 3-sat is hard in NP complete in the worst case, and we want to understand how hard is it on average. And in particular, in this talk, we'll focus on a particular problem. So as you add more and more clauses to the 3-sat formula, it becomes unsatisfiable because it's a random, you're adding random clauses. And so if you pick sufficiently many random clauses, it's unsatisfiable. So the natural algorithmic problem is to certify, to prove that the 3-sat formula is unsatisfiable, right? So, to formalize this, a certification algorithm is one which given a 3-sat formula, if it is satisfiable, it will reject it. If it is not satisfiable, it will accept it with probability at least a half. Okay, so it never accepts a satisfiable formula. So because it's a proof of infeasibility, but an unsatisfiable formula, it produces a proof or sort of accepts its probability half. So that's a certification algorithm. So you're trying to prove that a 3-sat formula is unsatisfiable. As you have more and more clauses, the problem gets easier. Because you have more clauses, it's easier to prove that the formula is unsatisfiable. So it's a heuristic observation that as the number of clauses increases, it's easier to figure out that the formula is unsatisfiable. So it's a, it's not only heuristic, I'm sure it's empirically also probably true that as you increase the number of clauses, refutation gets easier. So the question is, how do we actually measure it, or how do we actually study this phenomenon in average case complexity? The typical tools of complexity theory like reductions and so on are not well suited for this because it's very difficult to do reductions when your instance that you produce has to be uniformly random, right? So you need a different way to measure things. So, here's one possible thing we could do. So if you give me a 3-sat formula, you can, as you formulate it as a polynomial system or real numbers, right? So given a 3-sat formula phi, you can formulate it as follows. So if you have x, y, z, w as variables, you add these 4 constraints, x square equal to x, y square equal to y, and so on. X square equal to x ensures that x is 0 or 1, y square equal to y ensures that y is 0 or 1, and z is 0, 1, and w is 0, 1. So these are constraints that ensure that it's a Boolean, x, y, z, w are Boolean. And then every clause, it only involves 3 variables. So you can expect that there's a degree 3 polynomial that represents the clause. So in particular, every clause can be written as a polynomial equality in this case. So what we did was what I'm saying is that you can take a 3-sat formula and you can convert it into a polynomial system or real numbers. Not very surprising. And then we know that if the formula is unsatisfiable, then the polynomial system is infeasible. So we could study the SOS degree of this polynomial system. So it's an infeasible polynomial system. We could study what is the degree at which the system becomes infeasible. Okay, it's just a structural quantity associated with the polynomial system. So let's see what happens here. So we're going to look at a graph now. So we have the x-axis is the number of clauses. Okay, actually, there's a question. Yes. Sorry. Right. So the question is it simpler because there are no inequalities? Not really, because there are reductions that take inequalities to equalities and so on. So if there's an inequality, you can just subtract a little square, and then but it's a good question. It's nice that it doesn't matter whether you talk about equalities, inequalities, or strict inequalities, or so on. It's you can reduce between these things. Okay, so let's study the yes. Yeah.
Should be x times 1 minus y times z equal to 0.
Oh, yes, it should be x times 1 minus z times w. Yes. The second clause is wrong.
Okay, with the first one.
Oh, first one is also wrong. Okay. Oh, good. Thanks. Yeah. You see why I'm rushing through these slides very quickly. But good. You're all yeah. So okay. So here's what we look at. We look at how the complexity of this problem behaves as you increase the number of clauses. Okay. And on the x-axis, I have log of the number of clauses. On the y-axis, I have log of the complexity of refutation. But of course, how can I measure the complexity of refutation? It's like, what's the best algorithm? It's hard to do that. So we'll switch to SOS degree. But okay, around n clauses, once you have n clauses, the formula becomes unsatisfiable. So let's focus on the regime to the right of this line. You have at least n clauses, like order n clauses. Okay. So, and at the threshold, it's kind of believed that it takes exponential time to decide or refute formulae. And then as you increase the number of clauses, at n to the 3/2 clauses, like n to the 1.5 clauses, there's actually a very nice spectral algorithm. It's a by Feige, which solves the refutation problem. So, so then, we believe that as you increase the number of clauses, the complexity should decrease, right? So once you measure complexity in the terms of SOS degree, you actually do recover this line. If you plot the SOS degree of the 3-set of the polynomial system between n clauses and n to the 3/2 clauses in this log scale, it is a straight line. And there are both upper and lower bounds matching this up to, I'm only hiding log n, or in this case, log n in this picture. So this is a very nice outcome because it kind of, we are able to reason about average case complexity in a fairly satisfactory way. It's not as satisfactory as NP completeness because there's no complete problem, there are no reductions, there's no complexity class. But on the other hand, this is the best we can do at this time. And this particular picture has been extended to all CSPs now. Like in particular, for all CSPs, there's the characterization between, there's a precise characterization between SOS degree and the number of clauses. And moreover, this theory has been further extended to non-random situations. You'll probably hear about it in the workshop tomorrow. So which is, there are SOS-based algorithms for smoothed instances and also semi-random instances. Okay, so that's a success story. That's where things worked out well. So now I'll talk about two other situations contexts where there's still a lot of work to be done. So this is a fairly large class of problems called Bayesian CSPs. So let me give you a concrete example to keep in mind. So imagine you have n vertices and you sample a graph like this. You color the vertices from Q colors, right? Randomly, and you sample edges, order n of them, between the colors. So this is a graph with a planted coloring. It's a graph with a planted coloring. And what is the computational problem? Well, you just get the graph. Okay, you get the graph, which is just the edges. You don't see the coloring. And your goal is to estimate the hidden coloring. So estimate meaning, let's say even a crude estimate for the moment. So this is a planted coloring problem. So I'll go over a few of these problems that I call Bayesian estimation problems, and then define the class. So here's another problem. It's called a stochastic block model. So here you have n vertices, and every vertex is either blue or red, uniformly at random. And two vertices that are of the same color, of the different colors, have a slightly higher chance of being connected by an edge. So you sample a random graph where probability that an edge ij exists is equal to 100 over n if xi is not equal to xj, and is equal to 20 over n if xi is equal to xj. So each edge is independently present in the graph or not, and its probability only depends on the colors of the two endpoints. Okay, so that's a stochastic block model. And what you see is this random graph that is sampled from this. So, and then given this random graph that is sampled from this distribution, you want to recover the hidden coloring, the hidden partition of the vertices. Okay, again, it's an estimation problem. So, I'll give a slightly more general example. So let's say you have a signal, you have a n-bit vector x1 through xn. Okay, it's a Boolean vector, but you don't get to see the vector. You make observations of the vector, which are sparse functions on this. For example, in this case, you make observations which are like, you observe x1 plus x3 in a noisy way. So x1 plus x3 is 0, so you get 0. x1 plus xn is 0, but because of noise, you get 1. So basically, you make observations which are functions on constant number of bits. Okay, and these observations are noisy. Okay, so you have n hidden variables and you have observed variables. So this is precisely what a graphical model would be. So, and your goal is to estimate x given your observations. So to sort of keep yourself in the right frame of mind, the correct algorithm to think about here is what you do in a graphical model, which is to apply Bayes rule. If you had exponential time, the correct algorithm to do is to, given the observations, compute the posterior probability of x given the observations and sample from that posterior. That's the correct exponential time algorithm to think about. It's not an optimization. These problems are not optimization problems. These are really problems where your goal is to apply Bayes rule, right? And it takes exponential time to apply Bayes rule, and then we study complexity of this problem. Okay, so you can ask this question for any constraint. For example, I just wanted to show it here. You can ask this for not all equal to 3 sat. Not all equal to 3 sat is just a predicate on 3 variables, which is 1 if the 3 variables are not equal. And the situation is again the same. You have n variables, you make sparse observations, in fact, not all equal to of x1, x2, x3, and so on. These are sparse and random. Okay, that's basically the situation. They're sparse and random measurements, and your goal is to estimate the x given the observations. Okay, so that's the general problem. Okay, the reason I'm sort of setting up a general problem is because there seems to be some sort of a general picture for these problems. So that's why I kind of gave you a bunch of examples. And so in general, you have some hidden variables and you have some observations which are like linearly many, order n. They're random. They're local because they are on small number of variables. And they're kind of inherently noisy, meaning I don't mean you add noise to the observations. It's just that the observations do not exactly reveal the value of the variable, right? So, and the gold standard in this situation is to compute the posterior, compute x given O, which is do inference in this graphical model, or sorry, estimations graphical model, and you sample x from that. But we'll settle for something pretty weak in this context. Let's say we settle for, can you find any x that is better than random guessing? Okay, that's our computational goal. Like find me some x that is better than random guess. Alternately, can you distinguish these observations from completely random observations? Like, can you distinguish a graph with a planted coloring with a graph with no coloring? Just random graph. Okay, just a distinguishing problem of the recovery problem. Okay, so here again, you can study this problem as you increase the number of edges or the observations. So in planted coloring, as you increase the number of edges. And up to some point, it's actually impossible to recover the coloring. With very few edges, you can't recover anything. And as you add edges, at some point, it becomes statistically feasible, meaning if you spend exponential amount of time, it's possible to recover the coloring, but it might be computationally hard. And this is the region of interest for us. And then there's a regime at which it becomes computationally easy as you increase the number of observations. And the location at which the problem goes from being computationally hard to easy, that's the point which I want to pin down. And that's the point where we study average case complexity. All of these are average case problems. And there's a particular point in the parameter space, which is the only parameter here is the number of observations. Like it's like the degree of the random graph in the planted coloring or so on. And there's a point at which it goes from being easy to hard. And that's the point we want to study. And for this, actually, there's actually a fairly bold prediction already of where this location is, where the problem goes from easy to hard. And I just, sorry, I'm just bombarding you with the statement on the top, but don't read it. I'll probably try to explain it a few slides down. But first, let's just look at what it implies, because what it implies is already fairly impressive and surprising. So let's just look at planted coloring. For planted coloring, this prediction implies that the problem becomes computationally intractable precisely when the degree is more than q minus 1 whole square, where q is the number of colors. So if you had five colors, then precisely when the average degree crosses 16 is when the problem is supposed to become easy. And when the average degree is 15.99, the problem is supposed to be computationally hard. Okay, so that's the so that's the corollary of this kind of a boldish prediction. And you can sort of run this crank, and you can actually recover predictions for all kinds of, every Bayesian CSP or every Bayesian estimation problem. So in particular, you can ask, okay, I have not all equal to 3 SAT, where my observations are not all equal to clauses. Okay, what are the parameters? Like, there are two parameters. One is the number of clauses, and the other is the noise rate, like what fraction of clauses are satisfied. And you can ask at what values of parameters is this easy and hard. You can actually write a computer program that tells you exactly what the value of the parameters for which the problem is easy or hard. So that's what I've shown here. So it's kind of a bold prediction, but it's giving you very concrete predictions for concrete problems in average case complexity. And similarly, if you had a mixture of not all equal to 3 and not all equal to 5 clauses, you can do this, and you can keep playing this game. You can write a program that, given any Bayesian CSP, you can tell me what the predicted locations of easy and hard is. Okay, so let's see, how am I doing? Okay, so I think I'm going a little slow. I'll actually skip. I was planning to describe what that heuristic is, but let's skip that for now. We'll come back to this if there's time at the end. Okay, so this is a bold prediction. Okay, that's fine. What do we know about it? Well, we know that, firstly, there was an algorithm in the easy region. So here I've drawn a generic graph, but basically, if you give me any Bayesian CSP, there's a region where the problem is supposed to be easy, and there's a region where the problem is supposed to be hard. Okay, you can find out this region. And in the easy region, we have an algorithm for this problem from stochastic block models to coloring to finally to every Bayesian CSP. So for every Bayesian CSP, we know an algorithm that actually solves the weak recovery problem in the easy region. So in some sense, okay, that's in order to actually verify this picture, what we need to do is to actually prove that the problem is hard in the place where it's supposed to be hard. Okay, and yeah. So, okay, so now here is where sum of squares degree will show up. So we want to prove an average case problem is hard. We can't really do it, but we could instead use sum of squares degree to measure it. So here's what you would want to do. You'd want to show that the SOS degree is small in the easy region. And as soon as you cross from this easy region to hard region, the SOS degree shoots up. Let's say from 2 to cube root n or something. So your runtime goes from being polynomial to sub-exponential. That'll be great. Okay, but there's a big problem here. Firstly, how do you formulate a Bayesian CSP as a polynomial system? This is a little bit more non-trivial than usual, because if you try to cast the Bayesian CSP as an optimization problem like max cut or usually, It turns out that it doesn't even solve the problem in the easy region. So you want to write a polynomial system that actually solves the problem in the easy region, and then its SOS degree should blow up in the hard region. So we're able to write a polynomial system now, which solves the problem in the easy region. So I'll just quickly describe the polynomial system. It's very easy to understand. So it's called the local statistics polynomial system. So let's do it for planted coloring. You have a graph, and I have variables xi alpha, which is supposed to be whether the vertex I is assigned color alpha. Remember that in planted coloring, you're given the graph and you want to recover the coloring. So it's really, you're trying to write a polynomial system that kind of tells you the coloring. So it's natural that xi alpha is what you'd pick. So the question is really, what are the constraints? So the constraints are as follows. So let's take any two colors. Let's take blue and red. If you count the number of edges which have one endpoint as blue, another endpoint as red, okay, this is actually a degree 2 polynomial in these xij variables, xi alpha variables. In fact, I've written down the polynomial here. It is sum over all the edges xi alpha j red, I blue j red. Right? That's the number of blue red edges in this coloring. And what you want is this number should be close to the expectation. It's a statistic. It's like a statistic, global statistic. So it will concentrate. It will not be too far off the expectation. So what you'd want is that the statistic agrees with the expectation. So now we have a constraint now. Summation ij and e xi blue j red is equal to the expected number of red blue edges plus or minus delta n. And when I say plus or minus delta n, it's like two inequalities, one greater than, one less than. So we got an inequality out. And you can do this for all kinds of structures. Okay, of course, you can write a polynomial constraint for number of green red edges, or more generally, like number of structures where paths of length 2 where one edge is one endpoint is green, other endpoint is red, or the number of structures that look like this. Basically, all of these are local statistics. They count colored subgraphs in your graph. And if you write all of these local statistics constraints up to a certain degree, then you actually solve the problem above the computational threshold. In particular, for every epsilon, if you're epsilon above that blue, there's a boundary between blue and white, between the easy and hard. If you're epsilon above that boundary, then you just need to add these constraints for some constant C epsilon many subgraphs. Then the degree 2 SOS SDP on that, degree 2 sum of squares algorithm on that polynomial system solves the problem. So meaning this is a polynomial system where you just have constraints for all the local statistics. This polynomial system actually solves the problem at degree 2 above in the blue region where the problem is supposed to be easy. So yes. C epsilon is the size of the subgraph here. Yes. C degree depends on the number of colored nodes in the subgraph. It's degree 2 SOS. Yeah. Yeah. Because there are only 2 colored nodes in the subgraph. The subgraph can be large.
Okay.
Like let's say take a path. You count the number of paths of length 5 with one endpoint being red, other endpoint being blue. Okay, it is a degree 2 polynomial in the colors because only 2 colored vertices. Right. So that's why it's a degree 2 SOS SDP.
Thanks.
The question is, why is this a degree 2 SOS SDP? Although you're looking at large subgraph statistics, it turns out that all the subgraph statistics that we look at are non-backtracking walks of a certain length, and therefore, and only the endpoints are colored. So if I count the number of paths of length 10 with one being red, one endpoint red, another endpoint blue, right? That's a degree 2 polynomial in xi blue variables.
One to q, then it would be a q degree SDP.
No, the degree will just depend on no, degree won't depend on the number of colors, because as you increase the number of colors, you just increase the number of variables.
Yeah.
The degree just depends on the number of colored vertices in a given statistic. Okay, so so this is good. It gives us a polynomial system that works in the easy region. It doesn't yet say anything about the hard region. So here's a thing to do: prove that this polynomial system, its SOS degree in the hard region blows up, goes to root n or whatever. Let's say cube root n. So, and we don't. I don't have anything to report there, but it's like a future work or on. Yeah. Okay. Good. All right, so let me go to my third case study. So these things get increasingly more and more outrageous. So here's let me set up the situation. So let's look at hypothesis testing problem. What's a hypothesis testing problem? You have some distribution D over Boolean strings, 0, 1 to the n. And the hypothesis testing problem is you get a sample from distribution D or from the uniform distribution. And you just want to distinguish whether the sample is from uniform distribution or from distribution D. The classic example here is planted clique, where the distribution D is you take a random graph and you place a clique of size k. Think of k as square root n. So you have a random Erdős-Cheney graph and a clique of size k placed on top of it. So that's a distribution over graphs. So that is D. And then the hypothesis testing problem is really, given a graph, distinguish whether it's a random graph or a random graph with a planted clique. It's a uniformly random graph or from the distribution D. Okay. Okay, so for this hypothesis testing problem, there's a natural class of algorithm you could think about. These are low degree polynomials. So what do I mean? I mean the following. So you have a sample X, right? And you want to know if it's uniformly random sample or from distribution D. What you do is you take a low degree polynomial P of X, just one polynomial P of X, and you compute its value. Okay, you have a sample X, you compute P of X. Suppose the distribution of P of X, the value of P of X, when X is uniform, looks like this, just a picture. And suppose that the sample that you got from the planted distribution, P of X, is outside the bulk of this distribution. Meaning, whenever you compute, what I'm saying a little bit clumsily is that if the typical value of the polynomial under your planted distribution is kind of unusually larger than its value if X was uniform, then you would, of course, use that polynomial to distinguish whether the sample is from uniform or random. So it's a very simple class of algorithms, because I'm not allowing you to do anything but to calculate a single low degree polynomial and look at its value and see if it's unusually large. And if it's unusually large, you say you planted. If it's not, then say it's random. And of course, this class of algorithms would only work if the typical planted value is more than the standard deviation under uniform. Meaning, as you can see in the picture, the blue line, the planted sample, should be outside the bulk of the uniform distribution. Then this should work. So basically, if expectation of X from the planted X from the distribution D is more than the standard deviation of P of X and uniform, then this would work. I guess I'm assuming P of X, expectation P of X uniform is 0. Okay, so it's a very simple class of algorithms. And kind of the bold conjecture, low degree hardness conjecture, is that for sufficiently nice distributions, low degree polynomials are the optimal algorithms for hypothesis testing. Meaning these algorithms, that very simple algorithms, are really the optimal algorithms for this. Okay, let me, I mean, I stated this very imprecisely to sort of give you a feel, but now let me elaborate on the parts of this conjecture. So it says for sufficiently nice distributions, if degree D polynomials fail, then n to the order D time algorithms fail. Okay, that's the conjecture. What does sufficiently nice mean? So sufficiently nice is essentially two conditions. The first condition is that your distribution is symmetric under a large group of permutations. For example, if you have a distribution of graphs, right, of course, permuting the vertices, the distribution stays the same, right? Or a distribution of hypergraphs. Actually, I don't know, even if you had like a cyclic permutations, right, it might even be work. Okay, so that's one condition. The other condition is your distribution is noisy, meaning there is independent coordinate-wise noise that has been applied to the distribution. Like a coordinate-wise, there's some noise applied to the distribution. Okay, so here's the statement. For sufficiently nice distributions, if degree D polynomials fail, then n to the order D time algorithms also fail. And when we say degree D polynomials fail, it is exactly what we said earlier. Degree D polynomials fail if for every degree D polynomial, its typical value is smaller than the standard deviation, meaning its values on the planted don't stand out. Okay, so that's the conjecture. For sufficiently nice distributions, if degree D polynomials fail, n to the order D time algorithms fail. It's a fairly, as I said, the conjectures got more and more outrageous as the talk moved. In particular, kind of the most surprising aspect of this is that it's not been refuted yet. So maybe it's good to refute it, even in its strong form. Find refutations, find examples where it's false. There aren't many examples where it's false. So, in fact, its predictions agree with all the problems that we know algorithms for, like planted clique, random 3-sat, it will precisely predict that n to the 3/2 is the location where polynomial time algorithm should exist. For all the Bayesian CSPs that I talked about, the stochastic block models, planted coloring, all of them, those are also subsumed by this. And it extends beyond that to spiked matrix models, tensor models, and so on. So for a wide variety of problems, seemingly this conjecture seems to be true about their average case complexity. And I guess you can guess the kind of open question I'm going to pose here, which is the most natural one, which has been kind of around, is that, okay, prove this for SOS degree. It's hard to prove that n to the order D time algorithms fail, but it should be easier to prove lower bounds in SOS degree. So for sufficiently nice family of distributions, for sufficiently natural polynomial system, pick whatever you want, prove that degree D polynomials fail, imply that SOS degree fails. SOS degree is large. It's at least D over log n. Okay, I think I'll stop at this point. Yes. Right. So the question is SOS degree conjecture true for known problems? Yes. In all the cases that we know, in all the cases where we know SOS lower bounds, this holds true. Yes.
I'd like to ask whether there is any high-level reason why sum of squares technique is like better applied to average case complexity or in general probabilistic systems rather than pessimistic case complexity, for example.
Yeah, so yeah, so that's a great question. In particular, a glaring example of that situation is you look at CSPs. We have degree 2 SOS gives you max cut 0.878. And we don't have anything better at degree 4, degree 8, and so on. At least we don't know if we have anything better at degree. So that in fact is part of the content of the unique games conjecture. Yeah, so I don't have a good answer to that. But one answer I could give is that there are many ways in which you can sort of uh, defeat the SOS algorithm, as you can expect. Like one way is you can include some modular arithmetic in your thing. Like if it's a problem that can be solved by Gaussian elimination or F2, SOS SDPs will not work on it. So but there is some work by Venkat and so on who combine Gaussian elimination with sum of squares SDPs with linear programs. But yeah, it's a good question. I don't know why we don't have SOS based algorithm, that many SOS based algorithms for worst case problems. Yeah.
I have a question. So for all of these problems are like lower bounds known for like linear programming hierarchies.
Our lower bounds known for linear programming for these problems. I don't think they're written up, but I guess the reason the linear programming sort of is less attractive in this context is because a lot of these problems, the algorithm is spectral. So it's hard to, like the linear program doesn't even get close to the known algorithms. Like right, that's the.
But maybe like you may not, the range may be a bit broader, the boundary can be a bit broader. If you are using linear programming, it could be a weaker sort of result.
Right. Yes. Yeah. I don't know actually what's the threshold at which linear programming works. Yes. Yes.
We want to differentiate between two distributions, like the uniform distribution and a given distribution D. So there, what does it mean to for an algorithm to have time complexity?
Because your input is growing. The input is a n-bit vector. You can ask what's the runtime of the algorithm that does the distinguishing. I think the classic example to have in mind is this planted clique problem. So you're given either a random graph or a graph with a planted clique.
Yeah.
So the input is a n-bit vector, n choose 2-bit vector. And
Okay.
then
okay, fine. Yeah.
Yeah, in fact, so that's sort of the interesting thing about all of these problems from statistics, that there is an answer and you can find, we are in a regime where there is an answer, and if you just spend exponential time, you can find it. So it's really the computational complexity that we're interested in.
Okay. Thanks.
Thank you.
Yeah, can you ask him? Okay. ठीक है? Put it in the chat.
Oh, here. Now I don't know. It feels like you will shift around a bit. Test. Hello. Okay. This room is not so big. I think even without the mic, I should be able to project my voice enough. Oh, yes.
You say that. I think heard each other.
Yeah, that's true.
I was really surprised about the first time when I started talking. The person in the front couldn't hear me. I was like, it just doesn't look that far.
Let's start after 2-3 minutes.
Okay.
Minutes, right? It's just like, yeah, it's not like that. I'm just like, trying to get it done with this one. There's like nothing else.
Okay, so let's start the next session. Welcome to session A7. And our first speaker is Yen Hong Yao Alvin from NUS.
Okay, so good morning, and I'm presenting my work on maximum rank aggregation, and this is joint work with my advisor, Diptaka Chakraborty. Uh-oh. See if I can. Okay, we fixed it. All right, so first let me bring you through the paper title, right? So let me set the stage. So what is the problem of maximum rank aggregation? So let's say I have this Sn, which is the set of all permutations of length n, right? And for this talk, I will also just call them rankings because it's easier. Yeah. And we also have this D, which is a distance metric, and we'll talk about exactly what distance metric we will use next. And the problem of this maximum, or also called center rank aggregation, is to find some pi. Yeah, I've given S that contains rankings from my Sn, and I want to find some pi from my S that minimizes the objective value, which is the maximum distance of any input pi I to my pi, right? So here note that this pi does not need to come from my input S. It's anywhere in Sn. Yeah, but otherwise you can also kind of think of this as being like a special case of the one center problem where we are working on these rankings. Okay, so what distance metric will we use? And the most common one when working with rankings is called the Kendall-Tau distance. And simply put, is just the number of inverted pairs between the two rankings. So if we look at an example, I have this pi and my sigma here. So if you look at, say, the pair of elements 1 and 3, you'll see that in pi, I order 1 before 3. And if I look at sigma, I order 3 before 1. So this is what we call an inverted pair, because these two rankings kind of disagree on which is better than the other, right? So if you look at count all such pairs, then we get the Kendall-Tau distance. And if you look in this case of pi and sigma, the distance will be 4. Yeah. And the other thing we can see this Kendall-Tau distance as being is like this minimum number of bubble swaps needed to get from my ranking pi to my ranking sigma. Okay, so let's just look at a simple example of the rank aggregation problem. So let's say I have 4 inputs, pi 1 to pi 4, and I have like these 4 rankings. And I claim that the optimal center is actually just 1, 2, 3, 4, 5. And if you look at the distances of each of my inputs, pi 1 to pi 4, to my optimal center, pi star, we realize that, this center kind of tries to even out the distances to all of the inputs, right? Tries to sit somewhere to the center, doesn't make anyone too far away. So it's like we kind of have this distance of 4 to most of the rankings. And there's one that's closer with distance of 2, but yeah, we don't care so much about that one. Okay, and so this problem actually has lots of applications in things like voting systems, in databases, search aggregation, and so on, because you can see these rankings as being like some different inputs, right, of my rankings over some set of choices, like the students that we want to take in for our PhD program, right? Then you can have many different input rankings, different faculty have their own opinions and so on. And at the end of the day, we only want to have one single output. And this output should kind of represent the inputs as much as possible, right? Shouldn't be too far away from my inputs. So there are lots of applications of this problem. Oops. Okay, so what do we actually know, right? What do we know about solving or approximating this problem? Well, first, as you might expect, it is NP hard. But in the case for the Kendall-Tau distance, even when there are only constantly 4 input rankings, so I set the input number of input rankings to be only 4, it is still known to be NP hard. But it turns out that, well, things aren't so bad, as we actually have a very trivial folklore 2 approximation for this problem. We can just take the input, the ranking from my input, right, best from my S, that gives the minimum objective value. And this turns out to be a 2 approximation. And it actually works for any metric space because all we need is the triangle inequality to hold for this folklore approximation. Yeah. And also beyond just center, right, there's also this thing called the median rank aggregation problem. So it's also very well studied. And in this case, instead of the objective function being maximum, the objective function is going to be minimize the sum of distances for my pi, or for all my inputs to my solution pi star. And it turns out this median is kind of much easier than the center in the sense that we have known a p-task for this since all the way back in about 2005. But unfortunately for the center, we are still stuck with only the 2 approximation folklore algorithm. Yeah, so that's what our work tries to address. But unfortunately, it turns out that for us, the worst case turns out to be a bit too difficult, right? We just consider an arbitrary case where the inputs can be anything. It's still too difficult for us to try and break past that folklore 2 approximation. So we try and relax things a little bit. Instead of thinking about the worst case, we think about a more average case problem. So instead of my inputs being arbitrary, they are going to be generated from this probabilistic model that we call It's called the Mallows model. And how it works is that there's a hidden pi. So this pi is a ranking, and also a real parameter phi that's strictly between 0 and 1. And the probability that I sample any sigma from my whole space Sn is just given by phi to the distance between pi and sigma divided by the normalizing constant. So phi here is also known as the dispersion parameter. And why? If we look at this formula as phi tends towards 1, you realize the distribution we get is going to be very close to my uniform distribution. But if I let phi tend towards 0 instead, then the distribution I get tends to be very concentrated around my ranking pi. And it turns out, even in this simpler case, there's still nothing better than the folklore known. So that's where this work comes in to address the gap. So our contribution, so very simple, is just we give a p-task using O log 1 over epsilon samples that's drawn from a Mallows model that succeeds with some constant probability, at least 2/3. And here, we also note that the runtime is only polynomial in 1 over epsilon, so it's not exponential in 1 over epsilon. And so again, to emphasize, we do not know pi. All we get is just the observations, the samples from the Mallows model. We don't have pi. And also, I've kind of hand-waved away a little bit of the details. So there's some dependency on the dispersion parameter phi, as you might expect. But for here, we're just not so interested in it. We'll just focus on the epsilon for now. Okay, so let me bring you through, right? How do we come up with this p-task? Well, we have two main steps in our proof. So the first thing that we do is that we prove that this pi, the hidden ranking pi, is actually quite a good approximation of the center. And the second thing we do is that, well, we don't know pi, right? We like to find pi, but it turns out to find pi exactly, it's quite expensive. You need lots of samples. So instead, we're going to find some ranking pi c, which is quite close to pi. And then if I combine these two steps with my triangle inequality, then we'll have a good approximate center. Okay, but before we get into those two main steps, of course, we need some little lemmas to help us along the way. And in order to get those lemmas, we actually don't look directly at the Mallows model. We look at this thing called the repeated insertion model, which is equivalent to the Mallows model. The distribution that we get over the rankings is going to be the same. But it turns out that this repeated insertion model just happens to be easier to analyze. But the process is slightly more complex. So how it works is that I have some pi, right? And I want to sample a sigma. So I start with sigma being empty, and I'm going to iteratively construct my sigma. So I'm going to insert the first element of pi into sigma. I have one element in sigma. I'm going to insert the second element of pi into sigma. So now I have two elements in sigma, and so on. Yeah, and then each time we insert, we kind of define that we'll insert it into each of the different possible positions with like this given probability. So it's quite an ugly expression, but it's much easier to see with an example. So let's say my pi is just 1, 2, 3, 4, 5, and I want to sample some sigma. So at first, of course, if I place 1 into an empty ranking, the sigma would just be 1. And now I have two locations to insert 2, right? I could insert it before, or I could insert it after 1. And the repeated insertion model says that we will insert before 1 with probability 1 over 1 plus 5, 5 over 1 plus 5, and we'll insert it after 1 with probability 1 over 1 plus 5. So let's say we insert it, it ends up before 1 in this case. And now I have 3 locations to insert 3, right? It could be before, both of 2 and 1, it could be in the middle, it could be at the very back. So let's say it ends up at the back. And now I have 4 locations to insert 4, and so on. Yeah, so in some sense, the intuition why it's easier to analyze this repeated insertion model is that there's some kind of little bit of independence between the steps, right? Because you don't care what happened at the previous steps, the probability of where I insert my current element stays the same. Okay, so now let's talk about our 3 main lemmas. So we'll just quickly go through some of the ideas. So the first thing is something that we call bad pairs. So what is a bad pair? So let's say that my pi orders some pair of elements, A and B, such that A is before B. And then now let's look at my samples, right? So in this case, let's say pi 1 to pi 5, and 3 out of 5 of my samples order B before A instead. So that means my majority actually disagrees with my pi. So this turns out to be quite a problem, and so we call such pairs of elements bad pairs. Yeah, so the majority disagrees with my pi. And our main lemma is that, so it turns out there are not too many such bad pairs, and there's only e to the power of minus big omega of s n bad pairs with high probability. Yeah, so there's a little typo here. There should be a multiplied by n as well. Yeah, so it depends on, of course, the length of the permutation. Okay, then that's our first lemma. And the next one we show is that it turns out all of my samples, so for any pi I in my sample set S, with high probability, the distance between it and my pi is going to be really closely concentrated around the expectation. So you can think of phi over 1 minus phi n as like the expected distance of any pi I from pi. And we show that with high probabilities, well, any sample is going to be within a 1 plus or minus lambda band of the expectation, where this lambda is just a small o of one term. So it's really very close to the expectation. So we would expect things to kind of look like this, right? All of my samples, the blue dots, are going to be close to this expected distance to pi. Okay, and the final thing we have is that we show a simple lower bound on the optimal objective value of this set S. So we show that it's at least phi n minus some small o of n term with high probability. So effectively, what we show is very slightly stronger. We show that for any pair of elements, any pair of rankings, pi 1 and pi 2, that come from my sampled set, then there should be quite a large enough distance between them. And if they are far apart enough, that means the center also has to be decently large in terms of objective value, because the center has to be in the middle, right? So the objective value has to be half of this distance. Okay, so now with those three lemmas in hand, then we can finally move on to our two main steps, right? And the first one, we are going to prove that pi is a good approximate center of my sampled set. Okay, so how are we going to do it? Well, let's let pi star be some optimal center of my sampled set, right? So I have some pi star, and I also have my pi. And let's think about, right, they're both rankings. I can go from pi to pi star using bubble sort, right? So I can just treat pi star as having the total order of elements and just bubble sort. And each step of my bubble sort swaps a pair of elements, right? And in this way, you'll get something that looks like a chain of rankings, right? So I start with pi, I swap 3 and 4, I get this pi 1. I swap this 2 and 1, I get another ranking, this pi 2. And then let's say after that I swap 1 and 5, I will get a pi star. And each time, each of these intermediate rankings, we can think of what's their objective value as the center, right? How much better are we getting compared to pi? So each time we do a swap, we can characterize the swap as either being a bad pair or a good pair, right? There's the only two possibilities. So let's think about a bad pair. So suppose we have 3 and 4 is a bad pair. So in the very worst case, right, 3 is before 4 in pi, but all of my samples have 4 before 3. So if I swap 3 and 4 to get this pi 1, I reduce the objective value to all of my inputs. So my center objective value is certainly going to be better by 1 if I do this swap. So that's, the bad case for us, because pi star is going to be better. But what about when we do a good swap? Right? If we do a good swap, for example, from the pi 1 here to the pi 2, we have this swap 1 and 2. So if it's a good pair, 1 is before 2 in majority of my sample rankings. But now my pi 2 has 2 before 1. So in some sense, compared to the pi 1 or pi, I've kind of increased my distance to most of my inputs. So if I keep trying to make such good swaps, the amount of increase that's going to happen is going to outweigh the amount of decrease that happens. So we cannot improve our result by too much by just making some good swaps. So if we formalize these arguments carefully, we will show that the objective value of pi is at most the objective value of pi star. Okay, there's a small typo here. It should be objective value of pi star plus e to the minus big omega of s, so multiplied by n. So this is from the swaps involving bad pairs. So it's just equal to the number of bad pairs plus some small o of n term that comes from swaps involving good pairs. So this small o of n terms kind of comes from the fact that we have shown that with high probability, all of my samples have this closely concentrated distance around the expectation to pi. So that's kind of where that lemma comes in useful. And let's say I carefully set my S, so it'll be terms in the form of log 1 over alpha. I will reduce this to have a like additive approximation of alpha n over 3 plus small o of n. So now my pi is kind of quite good approximation for some small alpha. Okay, so that's our first step done. And the second thing we still need to do is to find my pi, right? Or more accurately, we want to find something close to my pi. And how will we do that? So here is where we have our one algorithm of this talk. So let's try and construct my pi c, which is close to pi. So what I'm going to do first is I'm going to build a graph G, which has a vertex for every element, right? So let's say I have 5 elements, 1, 2, 3, 4, 5, then I have one vertex for each. And now for each pair of elements, I draw an edge from A to B if majority of my samples order A before B, right? So if majority have 1 before 2, then I draw an edge 1 to 2. So now I have a complete graph, right? Every pair of vertices has an edge, and every edge is directed. And so in this case, we might have some bad pairs as well. So in this case, let's say 1 to 2 and 3 to 2 are both bad pairs. Okay, now because of these bad pairs, we may have cycles in G, right? If there were no bad pairs, then the G, the pairwise ordering would just follow the pairwise ordering of elements in pi. But because of bad pairs, well, this may not happen. So we may have some cycles. And the problematic part is that it turns out to find out the minimum number of edges we want to remove from this graph G to get an acyclic graph is the NP-hard feedback arc set problem. Yeah, but the good news instead is that there are very good approximation algorithms for the feedback arc set problem in complete tournament graphs, right? So we can even have a p-task for it. So let's say we just take the p-task and apply it as a black box on my graph G. And then it's going to give me some set of edges F to remove. So let's say let's say those two edges were 2 to 5 and 2 to 4. So let's say I remove them from my graph G. I get some graph G prime afterwards. And now I just take the topological ordering of G prime as my pi c. So in this example, we'll get something like 5, 4, 1, 3, 2. And here you notice that because we just take the p-task as a black box, we don't know what edges it will remove. It could possibly remove edges that are not bad edges, right? We're going to end up with some additional pairs of elements that in our pi c that don't have the same pairwise ordering as pi. So now if we take a look at this carefully, we'll see that, well, firstly, the p-task is going to do quite well in terms of number of bad pairs, right? Because if I remove all the bad pairs, then my graph is going to be acyclic. So that's our upper bound on the feedback arc set size. So we have like 1 plus epsilon prime due to the p-task as an addition for the size of my set F. And now, like I've argued for the past slide, the distance between pi and pi c is at most the number of bad pairs plus the size of F, right? In the very worst case, all of these pairs could end up being different in order compared to pi. And again, if we set S carefully, similar to the previous step, so it'd be some log 1 over alpha term, we're going to get that the distance between pi and pi c is just alpha n. Okay, so now let's put these two steps together by triangle inequality, right? So I have that the objective value of pi c is going to be at most the objective value of the optimal, right? So just opt plus 4/3 alpha n right? Because just now we had alpha from the first step, we had alpha n over 3, and then plus the small o of n from the first step. And now let's set alpha to be epsilon phi over 3. And then my whole thing will simplify to be at most op s plus epsilon phi over 2n. And then now, finally, we use the third lemma that my optimal objective value is going to be at least phi n minus small o of n. And I can go from this kind of additive form to get a 1 plus epsilon approximation of op. And here we'll use like O log 1 over epsilon samples. Okay, so where next? Where do we go from here? Well, naturally, the biggest question, right, is the one we kind of wanted to solve from the start, is to try and obtain a p-task for the arbitrary worst case scenario, right? So we don't have this probabilistic assumption on the input. So, but in this case, like you don't even need to get a p-task. Anything that's, better than the existing folklore 2 approximation would be like an amazing step already for this quite classical problem. And the second thing is that, so I've hidden it mostly in my talk, but our number of samples we need kind of has this significant dependence on phi, right? So we have this 1 over 1 minus phi squared term that comes in front of log 1 over epsilon. So this, if you think about phi, if it gets close to 1, the amount of samples we need will also kind of increase quite significantly. So can we kind of improve on this, right, and do better? Yeah. So that's our 2 main open problems from here, and that brings me to the end of my talk.
Thank you. So any questions?
In the step in which you deleted edges to make it acyclic, the tournament graph, why will only like even good edges could get removed in that step, right?
Yes.
Like, so then what if like most of the good edges get removed and only the bad edges remain or something like that?
Yeah, so let me check. Yeah, so the good thing is that there are not too many bad edges, right? And the number of bad edges is an upper bound on the size of the feedback arc set. So we cannot remove too many good edges as well.
All right. Yeah.
So you assume that you do not know pi, but
Yes.
you know phi, right?
Technically, we do not know phi either.
So that your algorithm doesn't use the knowledge of phi.
No, yeah, but we do need like enough samples. So like it needs to grow large enough. Yeah, with respect to the phi as well.
So
in
the
some
complexity
sense.
depends on phi, but the algorithm doesn't need to know phi. Is that
No.
correct? And is there any lower bound on the sample complexity?
Lower bound, no, we do not know like a lower bound if, the complexity. Yeah, but we think that, we already use only log 1 over epsilon, so that part seems quite good.
Yeah.
But we do not know anything better yet.
Okay, thanks.
Just pops down. Get to your Mac first, and then you have the dongle for the USB thing. For the clicker. Oh. So yeah, sorry. Put this up. Oh, sorry. Okay. It's the bottom one. Set up. Let's just it's already you might want to flip it.
Right. Can everyone hear me? Okay, okay. Yeah, cool. Oh, perfect. Thanks. No, that is absolutely the wrong slide to start at. There we go. Cool. Hey, okay. Thanks for coming, everyone. Today I'm going to be presenting some work on interval selection in data streams that I've recently been doing with Jacques Darc and my supervisor, Christian Conrad. So to get started, I'm going to go through sort of what the streaming setting is, then what the problem is, and then we'll start looking at what we've contributed towards this. So for those of you who don't know, the streaming setting's like a model of computation where we have an input, I, and our input is split into like m different parts. And you could sort of think of this as if you have an input in memory traditionally, these are like all your cells of memory and what's going on. And in our model, we're going to say that what if we don't have enough space to store our entire input? So we can't access it all whenever we want to. And instead, we have that our input is given to us sequentially in some order by some adversary or whoever. And we want to like store bits of this input using as little space as possible, and then compute some solution or approximate solution to our problem at the very end of the stream. So the fundamental idea here is we want to use as little space as possible, and we're allowed to use as much time as we want, given whatever we have in our space. So there's sort of two further subdivisions of the setting that are particularly relevant to this work. So in one setting, the insertion-only setting, we have that these elements of our input arrive, and then once they arrive, we've seen them arrive, we choose what to do, but they'll never disappear again. So think of this as I'm just going to give you the input one bit at a time, and that's it. And at the end, you have to output something. A generalization of this, which is slightly harder, is this insertion-deletion setting, where we can have stuff that arrives and also stuff that's deleted later. So when we see an arrival in this setting, we don't actually know if it's going to be part of our input in the end. It could be some other piece of information that's later deleted, and we'll have to deal with this. So just to summarize, both of these sound like both of these are exactly what they sound like. So when we work with these streams as well, we'll say n is going to be the length of our stream. Our optimum solution is going to be denoted opt. And in the insertion deletion setting, we consider this notion of the largest solution over all prefixes, denoted opt star. I'm going to say that's what that is for now. And then later on, when we come and look at some work in that setting, it'll hopefully become clearer sort of why we need that distinction and how that works. And so we can immediately come up with some trivial bounds for basically any problem of in space big O of n, we can do anything because you know the entire input and we can compute whatever we want in as much time. And trivially, we need at least enough space to store the output, because if we can't remember the output, we can't store the output. So we have these like really trivial bounds. And our key question in this setting for whatever we want to do is, what can we do across this regime? Like either exactly or approximately, as we said, just where are the boundaries for us? So this is the setting we're working in. And for this work, we're going to consider the specific problem of interval selection. So in interval selection, we're considered with intervals, and we're going to define an interval as a closed subset of the reals. And two intervals are independent if they don't intersect. This is exactly what you think of geometrically, where two intervals are independent if they don't touch each other or don't overlap. And the problem here is, given a set of intervals presented as some stream, we want to return a set of pairwise independent intervals, which is sort of as large as possible. Think of this as, alternatively, this is exactly what it sounds like, the independent set problem on intervals that we're trying to solve. So to kind of show what this looks like, suppose we have some real line here, we might have intervals arrive in sort of some order, and we want to compute something as large as possible. And in this particular example, the red intervals are a maximum size solution. So that's our setting, and that's our problem. And this is sort of the only thing we're discussing from here on out. So so we can kind of subdivide this field into what's happened in terms of like all of these different things. And I'm just thinking we'll start with sort of some existing work and then look at our contributions. So there's sort of two existing streams of work that have both happened independently. And one of them is kind of very much focused on the insertion only setting and upper and lower bounds there. And then there's another stream of work that's given us lower bounds in the insertion deletion setting. One thing here is we've seen, like we already have our trivial upper and lower bounds. When I present these numbers here, these are the approximation factors we can achieve within those trivial bounds. So all of our upper bounds have space dependencies on opt, not n. And all of our lower bounds kind of suggest that any approximation factor achieved that or better does just require us to store everything. And so first we see for the insertion only setting, we have this idea that in the unweighted setting, we can consider unit length and variable length intervals. And variable length intervals are harder than unit length intervals, and that feels quite natural. Somehow, unit length is like this additional constraint we've placed, and we can see that there's a 2 approximation barrier for variable length and a 3/2 approximation barrier for unit length. The weighted unit length lower bound I've sort of described here comes from the same work because it's inherited from the unweighted setting rather than explicitly being dealt with in its own way, which is great. In the insertion deletion setting, when we have this 2 minus epsilon approximation, this was a separate stream of work which was looking at the size estimation problem insertion deletion streams. However, the interval selection problem can be used to solve that problem, and so the lower bound extends across to this as well. So our contributions, our aims really are to just fill up the rest of this table, because that would be great, and we sort of do that. So we provide a 3/2 plus epsilon approximation for weighted unit length intervals in the insertion only setting. We show that weighted variable length intervals in the insertion only setting is just a difficult problem for which we can't achieve constant factor approximations. We then turn to the insertion deletion setting, so show that we can achieve stuff that's sort of tight to those lower bounds in the unit length setting, and then again show that the variable length setting becomes difficult in this insertion deletion setting. So this is what we're going to go through. As I do this, I kind of want to highlight that there's quite a few different things happening here, but a lot of the algorithms are kind of conceptually quite similar to each other, so hopefully the jumps aren't too big in the middle. So we'll start with sort of what's going on with the unit length insertion only intervals, and we're gonna do this with like an auxiliary lemma. And the idea here is we want to look at the subdivided regions of our space and then see how we can stitch these together. So I'll define a window of length gamma to be some set A to A plus gamma. So it's of length gamma. The really important thing here is we have one closed endpoint and one open endpoint. So yeah. And what we prove a slight generalization of this, and this as an idea does exist in literature as well. Is that if we can construct like algorithms that work in our restricted sort of windows, depending on the length of those restricted windows, we then naturally gain algorithms for unrestricted domains with like a approximation factor penalty that depends on gamma and a space blow up by big O of opt, but we know the big O of opt space is kind of optimal and tight, and we can't do better than that. So this is really nice because it lets us just consider an easier problem, right? So I'm not going to go through the proof of this now, but for some intuition of what these windows look like, if we have a real line and we're considering just gamma equals 3, what we're going to do is we're going to place down these numbers, and these windows are all going to be sort of touching each other. But remember, because we have a closed and an open endpoint, they're not intersecting. So they're all independent of each other. And then what I'm going to do is I'm going to shift over by 1, and I'm going to place down another set of windows. I'm going to shift over by 1 again, and I'm going to place down another set of windows. And I sort of keep doing this, and if gamma is a constant, I only do this a constant number of times. And the idea that we kind of prove and use is that you run all these instances in parallel, and one of these sets of windows will have a solution that is sort of good enough for our approximation, and that's where that comes from. So this is nice, because now we can only consider a single window of length 3, and that's a way easier problem, right? Like everything's gotten so much smaller. And in particular, our size of our optimum solution is now guaranteed to be 2, because in something of length 3 with an open endpoint, that's all you can fit. And so we can kind of think of it as we have the stream, we have a closed and open endpoint, we have a bunch of intervals, and in the unweighted setting, the algorithm is really quite simple. We simply store the left and rightmost intervals within this window, in this case, the 2 red ones. And so we have one approximation within this, like a perfect solution, and stitching it together gives us a 3/2 approximation overall. And this is the algorithm from literature. So we now want to extend this to the weighted setting. And the way we're going to extend this to the weighted setting is we show that you can simply subdivide these windows into geometrically increasing weight classes with sort of, I've drawn intervals here depending on like sort of their weights as they increase, and these are the weight classes they would be in. And the idea is we want to pick now the heaviest ones, right? And quite naturally, what we do is we run this algorithm in all of these. We can find a left and a rightmost one for each one and just output the heaviest out of all of those. And that's quite natural. We actually prove something slightly stronger, which is quite nice, which is that you actually don't need all of the weight classes in the setting anymore. What we observe is because the optimum solution is size 2, we either have one really heavy interval or like 2 things which both have similar weights. But if you have one really heavy interval and then one really, really light interval, the really heavy interval sort of contributes enough weight to be within sort of a 1/epsilon approximation of the sum of the two things if the second is really light. And so with some quite nice maths, which is in the full paper, we show that you actually only need to store this sort of log 1/epsilon over epsilon many of the weight classes. In particular, it's quite nice that somehow we now have an algorithm whose complexity is independent of the weights themselves, which is kind of neat. So we achieve this, and using the window lemma, we get our 3/2 approximation. So this is great, and we know this is tight because we know there's a barrier there. I'll now go through sort of our insertion-only variable length weighted lower bound, and we'll see that this is actually much harder than the unweighted setting where we were able to achieve a 2 approximation. So we're going to prove, so one of the standard methods for proving lower bounds in the streaming setting is just communication complexity, which someone mentioned yesterday as well. But I'll go over the game we're going to use and sort of how we use that game to prove this bound. So this is called the chained index problem. It was introduced by Kormo, Dark, and Conrad in 2019 in a separate paper on vertex arrival streams. And the game here is really quite simple. As an aside, if any of you are aware of the two-party index game, this can be seen as a multi-party generalization of that. And we have these players who each hold x vectors and sort of sigma indices. And our x vectors are of length k, and our sigma indices are indices in this k. And the idea is if we take any consecutive pair of them, the bit at that special index either has answer 0 or 1 because it's a bit, but all of them have the same answer. That's quite important. If they all have different answers, then it kind of becomes a little meaningless. And the aim of the game is to recover that bit value. And we want to do this using messages which are as small as possible. So in the two-party setting, this becomes the index problem, which is known and has like an omega of n lower bound. For the chained index problem, the best known lower bound is by Feldman et al. And they showed that you must send a message of size k over p squared, where p is the number of players and k is the size of the vectors. The proof of this, just as an aside, is quite information theoretic and non-constructive. So this is what we're going to try and use to do stuff. And so the way we're going to do this is, we're going to show that the protocol for interval selection can be used to solve chain k. So that way, the lower bound must transfer over, just because it's a new thing. And so our idea is we're going to encode our x vectors into interval things, nest these together in some way, and our aim is to produce a set of intervals such that the size of an independent set in this set of intervals encodes our answer bit to our chain k problem, so that if we had a protocol that could get a good approximation, we could then try and figure out what our answer bit was. And so our first step is going to be, given these xi vectors, we want to turn these into clique, like weighted clique gadgets, we call them. And this is kind of what that construction looks like, where we have all these possible like potential intervals. And I've drawn for the bit vectors that have the bit values that have value 1, we have a solid interval because the idea is the player just inserts that interval into the stream and that exists. And if that bit has value 0, then this dotted interval represents a position where we could have inserted an interval, but we've not inserted an interval. And so we can construct these gadgets for every single one of our xi's. The key now, which is quite nice, is because each player knows the special indices of the previous player, we can actually nest these gadgets within themselves. And this is where we're also going to use the fact that these are variable length intervals. So the idea is if we had like the first player has introduced this large gadget at the top, they have, okay, this is less visible than I thought it would, but suppose that middle interval was our special interval and it's highlighted red. The next player knows what that special interval was. They don't know which intervals have been inserted, but they know that special interval's location, and they find these two wing regions, which are these adjacent regions which intersect with everything else to the left and right, but do not intersect with the special interval. And they're gonna then construct these new child clique gadgets of their own, depending on their own x vector, kind of shrink them down to fit in this region and place them in there. And so this is kind of what the first and second players do. And then the ith player kind of recursively repeats this, inserting sort of more and more clique gadgets as we go along. And this seems quite neat, but it's kind of, the key is really how we consider it. And so the trick here is we now show that you can model the independent sets via a balanced binary tree. So there's a lot going on here, and I'll explain what's going on. Also, what I realized I haven't mentioned is, since we're in the weighted setting, player I inserts a gadget such that all of those intervals have weight 2 to the power of p minus I. So the number of gadgets geometrically increases, but also the weights of those gadgets geometrically decreases. And so the idea is the root node in this tree now, coming back to how we model this, corresponds to the gadget inserted by player 1. And then its 2 children correspond to this gadget inserted by player 2. And our key observation is if player 1 picks the correct interval, as in the correct answer bit, then that does not block anything inserted by player 2, and player 2 still has the freedom to pick intervals from both of those. But if player 1 picks the wrong interval in a sense and sends that along in a message, then that wrong interval will block out one of the subtrees of this gadget. And so we sort of kill off half of the tree if we make the wrong decision. And this argument recursively goes all the way down. And so by repeating this, we find that if the answer bit is 1, then we can pick all of those intervals which don't block anything. And sort of by summing over everything, we get that there exists a weighted independent set of size p times 2 to the power of p. And if they don't exist, we can't actually pick from the whole tree, and we can really only pick one path down the tree. And by picking that and summing over it, we get something of size 2 to the power of p. This gives us our result here, which is that a p minus epsilon approximation can now distinguish between the 0 and the 1 case, because if you, it just follows from what those approximation vectors are. However, we've seen that to do this, we then fall into our chain k lower bound of this requires our k over p space. But for any constant p, because we're talking about constant approximation factors, that just becomes omega of n space for us by sort of counting the total number of intervals as a function of k. And so any constant factor approximation just, unfortunately, is no longer possible in this setting. And with that, we've now concluded the story of insertion-only intervals. So this is quite nice, and I kind of want to stress as we go to the insertion-deletion setting, a lot of these ideas carry over. We just need to be a little more careful because we have deletions as well. So we'll start by looking at what happens in the unit length settings, bearing in mind that our lower bound is now a 2 approximation rather than a 3 over 2 approximation. So it's already got a little bit harder. And the key idea is we're going to consider a window of length 2 now rather than a window of length 3. And in our window of length 2, we'll have some intervals that arrive as usual. I'm not really sure why that's how it. But we're now going to have some arbitrary sequence of deletions afterwards as well. So this is why we can't store like a left and rightmost interval anymore, because if we did that, they could just be deleted later on, and suddenly we have nothing. So instead, our problem is now turned from, instead of recovering 2 in a window of length 3, in a window of length 2, we just need to recover a single surviving interval, which at first glance may or may not seem trivial. I don't really know. But what we're going to use now is there's a really nice problem in streaming called the L0 sampling problem, which sort of, I'm paraphrasing this, but roughly speaking, given an insertion deletion stream, just asks us to return a uniform random surviving element, which is like ever so slightly stronger than what we need, because we just need a single one, not a random one. But this will solve our problem. And quite nicely, Johari et al. Have shown that this can be done with high probability in space log cubed of n, which is polylogarithmic in n, which is kind of fantastic. So this basically yields, our algorithm where now we can just run these run an L0 sampler for every single one of these windows that has some surviving intervals. And so we have like a log cube blow up in our space, but we're fine with polylog factors because that's still significantly smaller than n. And we kind of using our window lemma from above, get that big O of opt factor as well. And this is where our 2 approximation comes in the unweighted setting. So the question now is, can we move over to the weighted setting in the same way? And it turns out we can, and the idea will sort of conceptually be the same. Again, we're going to subdivide into these geometrically increasing weight classes, as we did before. Life looks great. And so we have these intervals coming in, and everything seems fine. But now we run into a problem which we didn't have earlier, which is suddenly we might have deletions from the really heavy weight classes. And so what this kind of tells us is that earlier we were able to prune away the bottom weight classes because we knew that they couldn't contribute enough anymore. we can no longer do that because these weight classes might start to become relevant later on in the stream. So we're going to solve this by just saying we need to store all log W of them. Yeah. This same argument is actually also why we jump now from, as an aside, that space dependency I mentioned earlier, from opt being an optimum solution at the end of the stream to opt star being the optimum solution across all instances, across all prefixes of the stream. And we can sort of think of that as we could have a stream that looks like this, where lots of intervals come in and our optimum solution gets really big. But later on in the stream, an adversary starts deleting a lot of things, and the optimum solution gets a lot smaller over time. And so the optimum solution at the end of the stream might be really quite small. But at that earlier point in the stream with a really large optimum solution at the time, we had no idea whether or not these deletions would arrive. And so we sort of needed that much space in case that was the end of the stream to output the solution from then. It's an unfortunate lower bound we have to deal with. Yeah, sorry. So the question was if there's an adversary deciding what to do. Yeah, everything about this is adversarial. So the set of intervals we're given is adversarial, and the order in which we're given them is also adversarial. And we can think of it as being an adaptive adversary to all the algorithms we presented until now, and including this, are sort of strong against an adaptive adversary who's, just to be explicit, an adaptive adversary is kind of changing their inputs to the stream as they see what the algorithm is doing. That's the question? Cool. So we've shown that now we solved the same problem in the weighted setting with this log W over epsilon blow up instead of log 1 over epsilon, but that's fine. And so we've provided these results for the unit length insertion deletion setting, and we know that the 2 approximation barrier is tight, so that's sorted, and that's cool. Now we're going to go to our final set of results, which is going to be this sort of unweighted variable length setting, but in the insertion deletion setting. So we've seen that this is, again, easy and doable in the insertion only setting. Unfortunately, it will turn out to be hard here as well. And so we're going to use a very, very similar construction to what we did earlier. However, the game we play is going to be ever so slightly different. So instead of playing the chained index game, we now introduce the augmented chained index problem. For those of you who are familiar with index and augmented index, it's kind of a natural generalization in the same way. I said that as an aside, though. In reality, what happens here is we set up a chained index game as normal, but then each player is given this sort of X plus thing, which is an extra bit of information. So they know like sort of the prefix of everything the previous player has. So if the previous player has this vector X with special index sigma, they know all the values up to position sigma, but they still don't know position sigma there. And by a very, very similar proof to the one used for chain K, you can show that this problem has the same complexity. And so we prove quite simply that this also has the same lower bound that holds. And so we have an ever so slightly different game, but if we can use it, we'll still get hardness. And the idea is that these prefixes allow our players to introduce valid deletions into the stream. Because remember, it doesn't make sense to delete something that doesn't exist, but we can only insert deletions if we know what's been inserted. And so for an example, if we have this cleat gadget here with our special interval in the middle, the next player knows what the 2 intervals after that special interval are, and so can delete them quite easily. And this is a valid thing to do now, which we couldn't do earlier. And so the idea is we want to try nesting things in the same way again. But if we have this top level cleat gadget and the 2 upper intervals have been deleted by this augmentation, then suddenly we can still sort of nest on the left-hand side because there are intervals there which we can intersect with if we pick the wrong interval. But on the right-hand side, that no longer exists because this right-hand side sort of nested sub-gadget thing is actually just always independent regardless of what we do because we've just deleted all the intervals above it, right? They just don't exist anymore. And so we can't pick this out. Like, this doesn't give us anything anymore because we can always pick it. So instead, we introduce these deletions, but we can only nest on one side going all the way down. So instead of a weighted balanced binary tree, we now simply have a path, and our path is unweighted because all of our gadgets have the same weights. And so the conceptual notion we're going to use here is if we pick the correct interval from each thing, then we can pick an interval from every gadget along this path. And if we pick the wrong thing at some point, we've killed off the entire path, basically. And so we get that this kind of mirrors naturally to the answers of the bits, where we have these optimum size solutions, depending on what the answer bit is. And we notice, again, that this now tells us a p approximation requires us to solve the game, which is hard for constant p. Yeah, so that gives us our lower bound for these. Ooh, that's the wrong thing highlighted. That gives our lower bound for these unweighted variable length things. And what I'm going to say to that is, if the unweighted setting is hard, then the weighted setting must be harder. So we haven't explicitly covered it, but this weighted insertion deletion setting is also then just hard. So that kind of concludes the results that I wanted to present here today. Hopefully those algorithms sort of made sense. What's quite nice is that we have covered the whole table, and it kind of leaves us open to, so what are the future questions to ask here? Because there certainly are some. So what's quite nice is the interval setting is now well understood. But I think quite interestingly, in higher dimension geometric objects, that doesn't exist. Perhaps the most obvious one of these that's been asked and is in the literature is there's a well-known gap right now from the paper from CDK18, which is the same paper that introduced the chained index game, of for unit squares, there is a gap between the upper and lower bound. We have a 3 approximation big O of opt space right now using similar algorithmic ideas, but the current lower bound only is like a 5/2, which is a 2.5 approximation. That's still open. Obviously, further shapes are worth asking about too. This just seems like a nice starting point. Thanks. That's all I had to say. These are some references. There are more in the full paper. Thanks.
I have a couple of questions. So first of all, this setting is not the typical online setting, right? That
No, this
yeah,
is
just like it's not like irrevocably choosing the intervals.
So this is different because you're right. We don't
Yeah.
need to output something at every moment. We only
Yes.
need to output a solution at the very end of the stream.
Yeah.
But we still care about space.
Yeah. And so what is the update time per step?
So in this streaming setting, we don't actually care about update time. That's perhaps the
But
dynamic
it should be
setting.
logarithmic, right? Because when an interval comes, so for each window, you are just storing the sort of leftmost and rightmost. So when a new interval comes, you just need to determine the window in which it lies. Am I
So
right? Or,
yes.
so that is just logarithmic sort of.
What would it be logarithmic in?
Just like log n sort of the update time.
So I actually think it would be, as I think about this now, it would be constant time within the window, and you could find that window in constant time because you know the value of the thing and you know where,
Okay.
like you know where all the windows are beforehand. You don't have to search for it. You can just go there. So as I think about it now, you could probably do this in constant time.
Okay.
But I really, sorry,
Yeah.
I just briefly want to stress that in this setting, time is not our goal.
Okay. And in the insertion deletion setting, the 2 plus epsilon approximation which you showed, so that is an expectation, right? Or
This is all worst case adversarial, all of
Okay.
this. The randomized algorithms, the insertion deletion setting,
Yeah.
they work with high probability, and high probability here is like sort of 1 over polynomial in n. But nothing here is average case. It's
Okay.
all worst case adversarial.
and so in the insertion deletion setting, you maintained a uniform random interval up to the point you have observed, something like that you said. In order log cube and space, you maintain something.
Yeah. So this is, I think, asking about what's going on.
Yeah.
Talking
that's
about
fine.
this stuff.
Yes.
So perhaps we can talk more about L0 sampling offline.
Yes.
L0 sampling is really
Is
quite an
it
interesting,
just is it some variant of reservoir sampling or
not to the best of my knowledge.
okay.
But
fine.
I could be mistaken. My understanding is this really came from the core idea here is to split into sparse streams and then use sparse recovery algorithms, which are another well-known example, another well-known method within the world of streaming.
Does the lower bound for the communication problem hold against all protocols or for?
Yeah. This is for any protocol.
But why can't the, so could you please go to the definition of the communication problem?
Do you want to talk about the augmented one, or I guess it doesn't really matter.
Chain, the,
Where is it?
yeah.
It should be right here.
Yeah, so this, why can't P2 send sigma 1 to P1 and then?
So perhaps what I haven't made clear here is the game proceeds in one direction, and each player gets one chance to send one message to the next player after they've received a message from the previous player. So if we had multi-round stuff, then there are known results from the two-player setting that it does become much, much easier. And we can speak offline about this index trade-off result if you'd like. For us, though, in our sort of one pass, like if we have one pass of the stream corresponds to going through these players once in sequence. And then going back again would correspond to if we had another chance to go through the stream again.
All right, so P1 sends a message to P2, P2 sends a message to P3 and so on.
Yeah.
Okay. And is there a matching upper bound for this lower bound, K by P square, for this communication problem?
So interestingly, no. There are sort of two known upper bounds. There's a deterministic upper bound where every player can send almost nothing, and then player P-1 can obviously just send his vector to player P, and you have a big O of N upper bound. There's another upper bound which is sort of similar but not, where
So, sorry, what is N? There's no N here, right?
Oh, sorry, I mean K rather than N. Thanks. There's another protocol as well, which is known where each player sends a 1 over P sort of fraction of their input to the next. So we sort of independently try guessing every time. That sends the same total number of bits, but now each message has size K over P rather than K over down K. However, we note that that's K over P is still more than K over P squared, so there's still a gap there.
Yes. Okay. Thanks.
Yeah. There's one behind you.
Thanks. The last 5 over 2 lower bound that you stated on the last slide, is that also from a reduction from a variant of?
Yeah. So the 3 over 2 and 2 lower bounds come from the index problem, which is like the two-player version of chained index. That lower bound uses the chain 3 problem, so it uses like an extra player. However, it uses chain 3. It uses chain 3 rather than chain K, and so rather than chain P. Sorry. So since P is a constant, the lower bound is still omega of K rather than omega of K over P squared. There's quite a nice construction where you place unit squares within each other to try and make them overlap in some way, which is kind of the idea behind these reductions.
Thanks.
I don't really know why my screen has disappeared, but yeah. Sorry. There might be another question.
Okay.
Sorry.
So the complexity of the communication problem, is it the total length of all the messages sent or the length of each message? Or how is it defined?
So typically when we talk in the pure communication complexity setting, when we're working with those problems on their own, we typically care about the total cost. However, for us, the total cost sort of also implies a bound on the size of a single message. And the size of a single message is what implies a streaming lower bound for us. So
K over P square is the lower bound of the total cost, is it?
It's a lower bound on the size of a single message. So that would be a protocol that's, if there was a protocol that sends something K over P squared to every message, it would send K over P in total.
Okay.
Which is still less than what we currently have.
Okay, so K over P square is the lower bound on the size of a single message.
Yeah.
Okay.
To think about how this works in the streaming setting, the construction is sort of player 1 has their input, produces these intervals, runs the algorithm on their set of intervals, and then sends the state of the algorithm as their message to the next player. So that's why this lower bound message size is the lower bound on the memory required by the algorithm, because we keep doing this at every point, and at every point we need at least as much memory as the sort of lower bound on message size.
Thanks.
Yeah. Shall I take this off? It's really weird. Like when you're up here, you really can't hear yourself when you're speaking.
Hello. 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 Hello.
Welcome back, everyone. And welcome back to the last session before lunch. Our first talk for this session is by Rishi Saket, and he will be telling us about hardness of learning Boolean functions from label proportion.
Yeah, thanks. Yeah, so I'll talk about this hardness of learning Boolean functions. I think what is unclear here probably is what is this label proportions, right? Learning from label proportions. And there's joint work with Venkatesh and Guruswamy. So let me begin with the traditional model of learning, supervised learning. So this is called the probably approximately correct model. In this, basically, you are given a distribution from which you can sample training examples, which are basically feature vectors. These are just vectors and labels. And these labels are given by some unknown class of functions that you want to learn, right? And what you want to do is to efficiently output. You sample a bunch of these labeled points, and you want to efficiently output a hypothesis H, which agrees with the target function that you want to learn over that distribution with high accuracy. And you want to do this whole thing with high probability, and you want to have an accuracy which is like tending towards 1, right? And these functions here are basically some assigned for this talk. We'll just assume that they assign Boolean labels to d-dimensional real vectors or the d-dimensional Boolean hypercube, right? So if this can be done, then we say that the class of the functions f can be learned by the class of the functions, the hypothesis functions, right? For example, we know that OR can be learned by ORs can be learned by ORs, and similarly AND can be learned by AND. These are straightforward. Parity can be learned by parity, and linear threshold functions, that is half spaces, right, can also be learned by half spaces, LTFs, right? This is in the traditional model, right? But we want to look at a more a newer setting, slightly more general setting, where the labels of the feature vectors may not be available, right, for each of them, right, as individually for each of the feature vectors for training your model, but maybe they are available only as aggregates, right? And this can happen due to basically privacy concerns. You don't want to reveal the label of any particular feature vector. There could be some legal considerations. I mean, also there could be some cost to the supervision. So typically these points are labeled sometimes by some labeler, and that could be a costly affair. Maybe you can only afford some aggregate labeling, right? And this can occur in real applications. It does occur sometimes in medical applications where you have, let's say, a bunch of images or cells, and you only know the aggregate outcome of these things. There are some applications in physics where, again, because of some instrumentation limitation, you can only get some aggregate labels. And of course, due to privacy in many other applications, you have these lack of individual labels, but only aggregate labels. And so this can be this is formalized in this framework of learning from label proportions. And here the training data set basically has bags of feature vectors. These are just subsets of feature vectors, and for each of these bags, you are only given the average label of those feature vectors in that bag. So let's say you have 10 feature vectors. You're only told that, okay, 4 of them are labeled 1, 6 of them are labeled 0, but you don't know which one is labeled which, right? And your goal is still to train an instance level classifier or some model on this bag level training set, right? So your model should apply at the feature vector level, right? So that's still your goal, but you have this aggregated training data. Right, so this learning from label proportions, LLP, has been studied in the ML literature sort of as a niche area, but it is now becoming more and more important because of these some privacy considerations. Right, so what we want to study is how to learn these accurate instance level classifiers in this LLP setting, and we are going to look at worst case guarantees. So typically, how do you actually train your classifier, right? How do you train you have your training data, and pretty much what you do is you fit your classifier to the training data, right? I mean, you optimize your classifier to classify as much of the training data, and then because of some generalization bounds, you say that, okay, if there's a distribution, then whatever accuracy you achieve on the training data set is also true for, on that distribution itself, right? So basically you want to optimize on the training data, but now what is this notion of optimizing on your training data where you have bags, right? So what we look at is how well the hypothesis can classify these training bags, and let me just define this this notion formally. So you have this space of feature vectors, which is either the d-dimensional reals or the d-dimensional Boolean hypercube, and the bags, the set of all bags is basically all possible subsets. The class of function that you want to learn is a Boolean class mapping the feature vectors to 0, 1. And we define this label proportion induced on a bag induced by this function f, basically the average label of fx for all x in that bag, right? For every bag b, right? So you have these training examples, bag and its label proportion, which is consistent with I mean, the label proportions are induced by the unknown function, so it's a realizable case, right? And the goal is to train a hypothesis. You want to find a hypothesis which is as consistent as possible with f, but your consistency has to be measured on the bags, right? So so we say that the hypothesis satisfies a bag b if the label proportion induced by the hypothesis is same as that of the original function that you are given, the label proportion you're given. You want to match it, right? So that is the notion of bag satisfaction. It's a strict satisfaction condition that we are going to use. Yeah, and the goal is to, you're given these bags and the label proportion sampled from some distribution. You want to find a hypothesis that maximizes the number of satisfied bags. Of course, you could have a different notion of satisfaction or maybe consistency. Maybe you want to measure the distance between the label proportion, and some more general measure can be there, but this strict consistency makes sense for small bags, right? If you have a bag which is very small, you pretty much want to satisfy it, right? So we'll just stick to this notion. So this is the goal. So I mean, there is some previous work, not a lot of work in computational learning. So there was some previous works that I had the last couple of years. So which looked at the learning LLP learnability of half spaces, linear threshold functions. So here first, say, I mean, half spaces, as we know, can be learned to arbitrary accuracy in pack learning model, right? I mean, there's no issue, you can just solve a linear program. But here the problem is that, the linear program doesn't work. You can't write a linear program. So what happened? I mean, can you still do something? So it turns out that first of all, this problem becomes hard even when the bag size becomes 2, right? Not even larger bags, just bag size 2, it becomes a hard problem. So the first paper showed that satisfying even more than half fraction of all the bags of size at most 2 becomes NP hard, right? You can't find even if you're given a collection of bags of size 2, which can be satisfied by all of them can be satisfied by half space, you cannot find one which can satisfy more than half of them. You can actually improve that to 4 by 9. And then in the second paper, you also extended this hardness to larger bags, and basically the hardness factor, I mean, it becomes harder and harder, right? So it becomes, you cannot satisfy more than 1/q fraction of bags of size q. So this on the hardness side. And these papers also give approximations. So you can actually write a semi-definite program and use that to get this 40% approximation for bags of size 2. So this SDP, the first SDP for bag size 2 is sort of not that complicated, but then it becomes much more harder. And for bag of size 3 in the second paper, there was a 1/12 approximation, but a much more complicated SDP, right? And then for larger bags, actually it's open. You only get some weaker results. So the main thing is that this problem becomes qualitatively harder as soon as you have these bags instead of instances, where it is a very easy problem in the standard setting. When you have bags, it becomes a fairly complicated problem. Right, so in this work, we are going to look at the learnability of Boolean formulas, right? So the first thing that we look at is hardness of learning OR in this setting. Now OR is also can be represented as a linear, as a half space. So you can actually learn it using a half space, right? But let's say you want to learn an OR by OR, right? Then what can you do? So here again, let's say you have just bags of size 2, at most 2. Then our first result shows that it is NP hard to find a constant clause CNF, right, which includes an OR. So you have a CNF which only constantly many clauses. So it's basically an AND of ORs, and the number of hands is constantly many, but the ORs inside can be as large as possible, right? So, but you cannot satisfy even delta fraction of bags. So you cannot satisfy any constant fraction of bags because NP hard to do that, right? Even using an OR. And you can try to use some different type of Boolean function. So this is a constant width DNF. So basically it's a OR of terms. Each term is an AND, but the width of each AND is a constant, right? So this also is a generalization of an OR. So here you get a half plus delta hardness factor, right? And as I said, OR can be efficient. I mean, OR can obviously be efficiently learned by an OR in the usual pack learning setting. Also, you get a constant factor approximation if you are allowed to use a half space to learn an OR. That's by the that earlier paper. But then if you really want to just learn an OR by an OR or a CNF, a Boolean formula, then it becomes even harder. You cannot even satisfy a constant fraction of bags, right? And in the second result, you can think of it as a Boolean analog of like learning half spaces by polynomial thresholds, right? Degree D polynomial thresholds. I mean, sort of a restricted version of that. But for that, we don't know any hardness right now in the LLP setting. So note that here in the LLP setting, there is no noise, right? We don't need any noise to prove, I mean, it's not agnostic learning or anything. So it's a realizable case. The bags are always satisfiable, all of them by some unknown classifier that you want to learn, right? There are hardness results in the pack learning setting for linear thresholds using polynomial thresholds, but it's in the noisy case where you have some noise in the linear threshold. Yeah, so this is the results on learning OR, and then we also look at parity. So you want to learn a parity on bags, again using a parity. So here we look at like larger bags, constant size bags. So if you have, again, given these bags and the label proportions induced by a parity bags of size at most q, then what we show is that it is NP hard to find a parity satisfying q over 2 to the q minus 1, more than q over 2 to the q minus 1 fraction of the bags for any constant, plus delta fraction of the bags for any constant delta. And again, this is the noiseless case. So the parity can satisfy all the bags, but again, it becomes a very hard problem as the bag size grows, right? And then we also show an algorithm that can actually satisfy 1 over 2 to the q minus 2 fraction of the bags in polynomial time, right? Just some way of some sort of Gaussian elimination. Yeah, so in the next most of the remaining part of the talk, I'll sketch the proof of hardness of this reduction. Yes. So, I mean, typically many of the hardness reductions follow this paradigm of dictatorship test, and you combine it with some hard CSP to get your hardness hard instance. So the dictatorship test is basically a toy instance of the problem. In this case, this LLP parity problem on bag size q. So it is a toy instance of that in over some domain of Boolean vectors of dimension m, capital M, which is some large number, right? And it satisfies two properties. The first property is completeness, which says that for every I between 1 and m, there is a parity f sub I which can satisfy all the bags, right? So there's a dictator parity. So it just depends on that one coordinate which satisfies all the bags. And the soundness says that any parity which satisfies more than q to the q minus 1 fraction of the bags must be supported on a small set of coordinates, right? So that's the converse of completeness in some sense. So some number of coordinates, it just depends on, let's say, the bag size q and the delta, right? So we'll construct such a dictatorship test. But yeah, as I said, the hard instance is given by combining this dictatorship test with some CSP, in this case, what we call the smooth level curve. I'll not go into that. And you use this folding trick to incorporate the constraints of this CSP, this label cover. And yeah, you don't really have to do anything about the constraints of this CSP. You just need to do this dictatorship test because of this folding trick. Again, this has been used earlier in many works. Okay, so what is this dictatorship test? So the domain is this. I mean, the underlying set of feature vectors is this m-dimensional Boolean vectors, right? And you now want to create this toy instance, right? So it's just a distribution on bags of size q, and it is given by the following. So you choose a bag B of q feature vectors where and these are like m-dimensional feature vectors. So for each coordinate I, these q feature vectors satisfy the following property, that you are sampling the ith coordinate of each of them. So there are these this vector of length q is sampled uniformly from one of the coordinate feature vectors of dimension q, right? So it looks something like this. So you have x1 to xq as the columns of this matrix, and each row has exactly 1, 1, right? I mean, it's randomly sampled from a vector of just 1, 1 and rest zeros, right? Each row is sampled like that, and that's how you create this these feature vectors, right? And that's your bag. So you output this bag and give it the label proportion, target label proportion of 1 over q, right? So for completeness, you can clearly see that if you look at any coordinate, any row, and you give the, and you take the parity, which is just taking the assignment given by that variable, that coordinate itself, just the parity of just one coordinate, just that value itself, it satisfies all the bags, right? Because each row has exactly 1, 1 and rest 0, so the label proportion is 1 over q. Okay, so for the soundness, yeah, I'll just go over this proof, some part of this proof, which is sort of instructive, I guess. So assume that you have this parity, which is supported on the coordinates in the set S, where the size of the set is, let's say, capital K, and it is odd. I mean, you can look at the other cases, but the proof is almost exactly the same, right? So now if you look at a bag B, which is sampled from this distribution, and if you look at the parity of the assignments by this, I mean, the XOR of these assignments by this parity H itself, so you can just unravel it, and then it basically comes out to 1, right? Because in each so because then basically you're taking the parity of a subset of the rows in that matrix, and that the size of the subset itself is odd, and each row has exactly 1, 1, right? So it's basically you have an XOR of odd number of ones, and that becomes 1, right? So you have this, but let's say you are able to show that this h of x1 to h of xq, the distribution of this is close to the uniform distribution on the parity 1 subset of 0, 1 to the q dimensional hypercube. So let's say while the parity of the whole thing is 1, within that constraint, it's basically random. Let's say you are supposed to show, you are able to show this, then you're done, because what is the probability then that the label proportion is going to be satisfied? There are like q possibilities of getting a coordinate vector, which will give you 1 over q label proportion, but there are overall like 2 to the q minus 1 possibilities, so you get q to the q over 2 to the q minus 1, which is what you wanted, right? So the key thing is to show this, right? So how do you show this? So it turns out that it suffices to show that if you take any subset of these of this vector, I mean, and then so that subset is of size t, such that its size is at most q over 2, right? If you take this and look at just the XOR of those hxj's for j in that subset t, then the probability that XOR is equal to 0, basically that is unbiased. You want to show this, right? It is roughly, I mean, more almost unbiased. If you show this, then you are done. Turns out this is enough for that. There's basically some sort of variant of Vazirani's XOR lemma that you can apply, right? So basically you want to show this. So you define this variable zi, which is just you take, you're basically summing up the rows the rows in S, but only the columns in T, right? So that particular rectangle in that matrix you're summing up, and that's Zi. Sorry, the ith row and the columns only in T, right? So the whole thing is just summing up all the rows in S, but Zi is just summing the ith row and the columns in T. So now if you look at it, right, so in that row you had exactly 1, but it could be like at a random place, and now you have only columns in T which are only R columns. So the probability that you are 1 is R over Q, and 0 is 1 minus R over Q, right? And each of these things are independent. These Zi's are independent, and the actual parity that you wanted to look at is just you're going to take the XOR of those rows of the Zi's of those rows in S, right? So this is what you want to show is basically unbiased. And to show this, you just have another way of sampling these Zi's. So what you do is that you first sample a subset of S by choosing everything IID with probability 2 times R over Q, right, which is at most 1. And then in each I in that subset, you set Zi equal to, outside the subset, you set Zi equal to 0. Inside the subset, you set Zi equal to 1 with probability half, and with probability half set it to 0. Now it's easy to see that as long as this subset U is non-empty, this parity is unbiased, right? So what's the probability that this is non-empty? I mean, this is a straightforward calculation. You have the size you're choosing out of the subset S, which is of size K. The probability that it is empty is 1 minus 2 R over Q, because that's the way you're choosing the subset to the K. And then basically you actually want it to be something like delta divided by 2 to the Q, something like that. And for that, you only need to have this capital K bigger than some function of Q and delta, which is something like Q squared plus Q times log 1 over delta. So basically it's a straightforward calculation. So it is basically unbiased, right? So you're done with this proof, and yeah, I mean the whole thing goes through. Yeah, I'll talk just a bit about the results on OR, the hardness results on OR. So the hardness reductions are adapted from this paper from some time ago. This paper studied hardness of learning 2-term DNFs using constantly many DNFs, and also noisy ORs using these constant width DNFs. But the thing is that when you have these bags of size 2 even, right, you can, instead of the 2-term DNF, you can basically incorporate that into the bag size, right? And you can just get the hardness for OR, and there's no noise also needed, because again, that can be incorporated in the hardness reduction. Whatever uncertainty that you need can be incorporated into this bag. Right? And there's an additional trick so that, so in this you get, in this paper you had hardness factors of half plus delta. For the first result, there's some additional trick which you use to get a hardness factor of delta instead of half plus delta, right? And yeah, basically the reduction is using a dictatorship plus a consistency test on these label cover edges. You use the bipartite label cover and some neighborhoods, right? Okay, so probably a bit early. Yeah, so let me go to future work. So while there are hardness results in this paper, there are many algorithmic guarantees that are not known for LLP learning ORs, right? So can you actually, for example, that half plus delta hardness, can you actually satisfy half of those bags using constant width DNFs? Not clear. What is the approximation that you can get? I mean, it may be some sub-constant factor, but can you get algorithmic guarantees for learning an OR by an OR and things like that, right? In the worst case. And of course, for parity, there is a gap between the algorithm and the hardness. So can you close that? Other concept classes. So this whole thing is actually open, because these and the works that I mentioned are the only ones that have studied this LLP thing in the computational learning setting. So pretty much whatever people have done, you can try to do in this bags, right? And also you can try to look at in learning in this setting. Pack learning is basically what I'm saying is that you can try to get arbitrary accuracy results when you have distributional assumptions, right? So if you assume that the feature vectors are coming from some good distribution, bags are sort of random, can you do better, right? So we had a recent result in which we looked at the packed learning of these half spaces from random bags, and when the feature vectors are Gaussian, and there actually you can recover the half space with high accuracy. I mean, you can basically get arbitrarily close to 1 accuracy, basically packed learning bounds you can show. Right? But then again, it's open for many other classes, the whole thing. Thank you.
I mean, there is time for a couple of questions.
So just regarding the half plus delta result, so with the DNFs, you don't know whether that's a natural threshold, right? That's what you mentioned.
At least I don't know if that is possible. I mean, algorithmically, if that's right.
And you said if you go all the way to LTFs, then you do have like 2 by 5.
2 by 5, you have. Yeah.
Okay, so is there like a, I don't know, an intermediate expressive class that you could look at to get like a constant factor approximation, a natural thing?
I mean, it's not even clear that if you use polynomial thresholds, can you exceed 2/5? I mean, you need to exceed 2/5.
Right, not just to achieve a constant factor. Just thinking.
Not clear.
So what if you did, I don't know, just from a circuit complexity point of view, look at like general DNFs or maybe even larger depth Boolean circuits or something?
I mean, yeah, that's all open, I guess. Nobody has done that.
Okay, then let's thank the speaker again. Okay, so last talk of this session is by Nicholas, and he's going to tell us about de-randomization of orthonormal protocols.
Okay, thanks for the introduction. This is joint work with Dieter, my advisor, and now I'm going to talk about every single thing in that title, right? In order, hopefully. Okay, so in computational complexity, a very important open problem is if we can simulate randomized algorithms deterministically with just a little overhead in time. And in terms of complexity classes, this is asking if BPP is in P, right? And there are a lot of connections between this question of de-randomization, pseudo-randomness, and lower bounds. And there's been some recent progress on these connections. And our results are similar in this sense, but to proof systems instead of randomized algorithms. And there, in the case of proof systems, we're asking instead if the class AM is an NP, right? So soon I'll define this class. So the outline for the talk, I'm going to start talking about these connections between de-randomization, pseudo-randomness, and lower bounds. Then I'm going to talk about these Arthur-Merlin protocols, and then those same things, but now for Arthur-Merlin protocols, our results, and some proof ideas. Okay, so let's start with pseudo-randomness and de-randomization. So say we have this randomized algorithm A, right? And we want to de-randomize it somehow, right? So it receives an input X and produces an output. We can view the randomness for this algorithm as an extra input, R, like just its random string, that it uses to produce its output. So a very common way of trying to remove the randomness from this algorithm and simulate it is to use a pseudo-random generator, right? So this is an algorithm, G, that produces a sequence. Is this working okay? Okay. Produces a sequence of strings that approximate the acceptance probability of this algorithm A, right? So instead of giving it truly random bits, we give the algorithm these pseudo-random bits and then simulate it on all inputs. And these objects are sufficient for de-randomization, but it's unknown if they are necessary for de-randomization, right? So they may be way too strong for what we are using them for. Okay. There's a variant of these objects called a targeted pseudo-random generator. So this object is, again, an algorithm G, but it gets to see the input where we're trying to de-randomize algorithm A. So it receives X as an input, and it only needs to produce a pseudo-random sequence for that particular input. So that's why it's a targeted generator. And interestingly enough, it was shown in 2011 that these objects are not only sufficient, but required for de-randomization of the class BPP, right? So they fully capture the task of de-randomizing BPP. Now let's talk about some of the connections that these objects have with lower bounds. So the PRG is the first object that I talked about. They're equivalent to the existence of explicit Boolean functions that have high circuit complexity. So in a specific parameter setting, the one we're talking about, we have the following equivalence, right? So the existence of these objects and linear exponential circuit lower bounds for problems decidable in linear exponential time, right? So you have these problems in E that require circuits of size 2 to the epsilon n. Okay. The recent progress that I talked about connects de-randomization with uniform hardness assumptions. So no longer against circuits, now against probabilistic algorithms, right? These lower bounds are now for functions with more output bits, not just one. And they are also for a stronger type of lower bound, which is on almost all inputs. So Chen and Tao quite recently obtained a near equivalence in this setting. So they showed implications on both sides, but not yet a full equivalence between hardness and de-randomization. But this year, Liu and Paz obtained a full equivalence with a stronger hardness notion, which is leakage resilient hardness. Right? So what does this equivalence look like? Right? So let's look at their result. What they show is that there's an equivalence between full de-randomization of BPP and the existence of this function that's length preserving. It's computable in polynomial time, and it's hard for a certain class of algorithms, right? So this class of algorithms is algorithms that are faster than the original one, probabilistic, and they also get to see some information about the function f, right? So they receive what we call leakage on f, right? In this case, n to the epsilon bits. So let's explore this notion of leakage resilience, right? So usually we have an algorithm A, it receives input x, and we want it to output f of x, right? That's the usual notion of computing a function f of x, right? In the leakage resilience setting, we have an extra algorithm. It's called leak, right? It also gets to see the input, but it gets to see the entirety of f of x too, right? Now the thing is, it can't feed all of that to A because then it's trivial to compute f of x. So it gets to reveal some information about f of x, but not a lot, right? In this case, in the case of the result, some subpolynomial amount of information, right? And then to get de-randomization, we want this pair of algorithms to fail, right? So we want the output to be different from f of x and on almost all inputs. So, if we fix a pair of algorithms, we want them to fail to compute f of x on almost all inputs or succeed only on finitely many, right? So that captures the Liu-Paz result. Okay, now let me talk about Arthur-Merlin protocols. So to talk about them, I'm going to start with interactive proofs. And to start with interactive proofs, I'm going to start with the regular notion of proof, which are problems in NP, right? So one way of viewing the class NP is as follows, right? So we have a verifier, right, which here kind of looks like Arthur. So this will be our Arthur in the future, right? And we have a prover that's going to give us the proof, right? So usually it's just an existential quantifier. There is a witness, there is a proof, but we can think of an entity that provides this proof, right? And then in the case of NP, both of these get to see the instance X, right? Merlin provides a proof. Notice that the prover here, or Merlin, is not computationally limited in any way, right? So he gets to solve this NP-complete problem, give you the proof, and then the verifier makes a verification and accepts or rejects. To go from this to interactive proofs, we introduce two things. So the first one is randomness. So we give the verifier, a coin. Now he gets to toss some coins, get random bits, and use them in the verification process. And we also introduce interaction, right? So now, instead of just having this one-way communication, the verifier gets to ask a question, the prover replies, ask another question, and so on, until the verifier gets to acceptance or rejection, right? And then now the idea is that if X is a true instance, then there should be a prover that convinces Arthur, right? That convinces the verifier with high probability, and it can be even probability 1 in this case without loss of generality. And in the other direction, if the instance is false, then no prover should be able to convince the verifier with high probability. Okay, and when we have a constant number of rounds in such a proof, we actually have a canonical form for these protocols in in the form of an Arthur-Merlin protocol, right? So why Arthur-Merlin protocol? Because once these two get the instance X, Arthur goes first, and the only message he sends are some random coins, right? So he tosses some random coins and sends that information to the prover, who then replies with a message, and that's enough to get into acceptance or rejection, right? So if you have a constant number of rounds, you can collapse it to just 2 with Arthur going first, right? Okay, so now I talked about introducing randomness to obtain these interactive proofs. Now let's talk about removing it, right? So if we're thinking about getting rid of the randomness in such a protocol, it's very natural to try and employ some type of pseudorandom generator construction, right? So we could give Arthur a pseudorandom generator. He uses those to obtain pseudorandom strings, and then runs the protocol with that pseudorandom string, right? And of course, it could be a targeted generator as well, right? So a generator that also gets to see the instance X. Okay. And when we do this, right, when we remove randomness, we go back to NP, right? So now we just have non-determinism in Merlin's message. Okay. So in the regular setting, it turns out that this object called the hitting set generator, which is a pseudorandom generator that's suitable for algorithms that only make mistakes on one side, right? So this is because the error can only happen in false instances. They are sufficient for de-randomization of Arthur-Merlin protocols. And just like in the BPP setting, it's open if these objects are necessary, right? Similarly, in the targeted setting, these targeted generators are sufficient for de-randomizing AM, but it's actually still open if they are necessary, right? And this was posed as an open problem in the 2011 paper that proved the equivalence for BPP. Okay, so just like in the BPP setting, regular hitting set generators are equivalent to circuit lower bounds, but this time against non-deterministic circuits. So following theorem by Milterson and Vinochandra presents an equivalence between the existence of these hitting set generators and essentially the same circuit lower bound as in the BPP setting, but introducing non-determinism on both sides, right? So now the class is a non-deterministic analog of E, and the circuits are non-deterministic, right? And there's been some recent progress trying to solve this open problem of connecting targeted generators and de-randomization for these objects. Myself and Dieter, earlier this year, obtained a first step in showing that these objects are necessary. So if you have de-randomization, you get some targeted generators back, but they're not as strong to obtain the de-randomization back, right? So it's a relatively weak result, but it shows that they are at least necessary. This work, we show a full equivalence between these two, but for a weaker form of de-randomization that we call a mild de-randomization, that I'm going to talk about soon. And similarly, we may ask about hardness assumptions that are equivalent to de-randomizing Arthur-Merlin protocols. And again, same work earlier this year. Myself and Dieter obtained a near equivalence between full de-randomization and hardness assumptions that work on almost all inputs. And in this work, we again obtained a full equivalence in the mild setting, right? So now, what do I mean by the mild setting of de-randomization? So in the case of BPP, because we believe, for example, in those circuit lower bounds, we believe that BPP is in P, right? And this would be a full de-randomization for the class. But it's actually open whether BPP is in NP, right? So one level up in introducing non-determinism. And not only that, this question is open even for sub-exponential time. So we can even separate BPP from non-deterministic exponential time. It's a relatively embarrassing problem, open problem in computational complexity. So for AM, again, we believe that AM is in NP, but we can't show, we don't know yet if AM is in this class, NP with a satisfiability oracle, or sigma 2P, which is one level above NP in the polynomial hierarchy, right? And this is the mild de-randomization setting. Just like in the BPP setting, it's open even for sub-exponential time, like very weak de-randomizations are still open in this setting, right? So with all of that, I can finally talk about our results. So like I promised, we have this full equivalence between mild de-randomization and the existence of targeted hitting set generators that achieve this de-randomization result, right? And not only do these results apply to this class NP with a satisfiability oracle, it also applies to some intermediate classes and to slower de-randomization. As for the second result, we connect mild de-randomization with leakage resilient hardness, and we show that a mild de-randomization for AM is equivalent to the existence of a length preserving function, right? This time it's computable in this class, sigma 2P, right? And it's hard against algorithms that also get a satisfiability oracle, right? Probabilistic algorithms, with the only requirement being that they must have non-adaptive oracle access. So they must ask all of their queries all at once. Now, and again, it also extends in the same way. Okay, so let me just mention that this notion of leakage resilience extends very naturally to algorithms with satisfiability oracles, right? So in the BPP setting, remember we had these pair of algorithms and we wanted them to fail, right? So now the only change is both of them get access to a satisfiability solver and we still want them to fail, right? Just remember that this access is limited in a certain way, right? So they can't get to query it adaptively. Okay, so let's get into some of the ideas that go into proving these results, right? And the first idea is actually an old idea, which is employing these pseudorandom generator constructions that are based on circuit lower bounds, right? So what we have is we start from the truth table of a hard Boolean function and use it to build a generator, instantiated with that hard truth table, right? So then, the generator gets to use the truth table to come up with the pseudorandom strings and then try to fool this algorithm A into thinking those outputs are actually random, right? And the idea is that if the circuit complexity of this particular function is high, then the pseudorandom generator is going to work, right? It's going to fool this algorithm A, right? But if you examine the proof for this last statement, it's not actually in this direction, but the proof is in the contrapositive direction. So what is shown is that if the pseudorandom generator is not good enough, like its output is not pseudorandom, then there exists a small circuit that computes the truth table, that computes function H, right? So it has low circuit complexity. And not only that, these proofs are generally reconstructive and learning, right? So what do I mean by both of these? So let's think about, say our generator fails to fool a particular algorithm A with an input X, right? So we package them together and call this our distinguisher, right? And because the generator is based on this function H, we can see that this distinguisher is revealing some information about the function h that we're going to use to compute it more efficiently, right? So then we're going to feed this distinguisher as input to a reconstruction algorithm that's going to produce the small circuit, right? But to produce the small circuit, it needs some extra information, right? And that's where the learning property comes into play, right? So not only it looks at the distinguisher, it gets access to some evaluations of this function h, and then it learns a small circuit for function h, right? So from these two, it produces the small circuit, right? Okay. So how do we connect this to leakage resilient hardness, right? So say we have our leakage resilient hard function, right? Call it f. And we want to construct a targeted generator using f, right? So general idea is to employ this some reconstructive generator with some function h sub x that depends on x, right? Remember, this is fine now because we're building a targeted generator, so it can have different outputs for different targets, right? In this case, the function is relatively simple, right? It's just we take h sub x to be the function whose truth table is f of x. So yeah, so the construction for the targeted generator is c's input x and outputs g of h sub x, right? Where, again, h sub x is the function with truth table f of x. Okay, now let's say it fails. We want to show that our hardness assumption fails too, right? So we want to show that we can compute function f with a small amount of leakage on input x. So because we have input x, we can obtain the distinguisher, right? Remember, it just depended on x and some algorithm that can be hard-coded into the construction. And access to f of x is enough to answer all of the learning queries, right? So remember, we need to look into some pieces for the function, and we actually get to, right? Essentially for free, which allows us to run the reconstructor, and it produces this small circuit that computes the function h sub x, which we finally evaluate at every point to compute its truth table and recover f of x, right? So in the leakage resilient setting, we can view the reconstructor as the algorithm leak, right? So it gets to see f of x, and it outputs this tiny circuit, which is the leakage, which then this algorithm A gets to evaluate, right? Okay, so this strategy requires a choice of reconstructive generator, right? And Liu and Paz used the Nissan-Wigderson generator, very classical construction, and with a known learning reconstructor algorithm. Right? For our work, we employ a non-deterministic version of the Chaltiel-Humans generator, and also a recursive version of the Miltersen-Vinochandran generator for some extensions. And then I'll just mention that the main technical contribution is developing learning reconstructors for these generators, which were previously unknown, right? So we show that they obey that property of being able to learn a small circuit for function f. And up until now, everything I said actually applies to NP as well. So if you assume some sort of leakage resilient hardness, you actually get full de-randomization. So why do we only get mild de-randomization, right? And the reason for this is in the other direction, right? So now we need to go from de-randomization back to hardness, right? And the argument there goes more or less like this, right? So first, a random function is going to be leakage resilient hard with high probability, right? Essentially because it's going through a compression phase and you cannot compress most strings, right? Even if you give these algorithms an oracle for satisfiability. Now, to test if we have a good choice, so say we sampled a random output and we want to check if it's good, we can actually do this in this class BPP with a parallel oracle for satisfiability, right? So now what we want to do is de-randomize this construction because we're assuming de-randomization, right? But the problem is we want to de-randomize this larger class, but we can only assume de-randomization for AM. Right? So our second technical contribution is we showed that in the case of a mild de-randomization, we can extend a de-randomization for AM into one for this potentially larger class. Right? So let me just mention, for example, that this class contains P with a parallel set oracle. So we don't believe we can collapse this into NP, right? So that's why this argument fails in the traditional setting. Okay, so now just to conclude, right, we've seen that the existence of targeted generators is equivalent to mild de-randomization for AM. Same thing for this notion of hardness, of leakage resilience. And perhaps the most important open problem here is what about full de-randomization, right? Can we get some equivalence there, either with some type of pseudorandom generator or with some hardness assumption? And also in the AM setting, there's more hope for obtaining unconditional de-randomization results, right? So another open question here is, can we use this characterization to help us show that AM is contained in some smaller subclass of, in this case, sigma 2, this exponential version of sigma 2. And that is all. Thank you, everyone. Are there any questions or comments?
Questions?
Yes, so you have a slide on the targeted generator, I think.
Okay.
Where you
near the beginning?
Maybe the middle, like the equivalence between yes, this one maybe.
Okay.
But you say so you give a specific definition of a targeted generator, or maybe it was leakage resilience, one of the two. And so basically you say it's equivalent to AM being in NP to the SAT. And my question is, if you were to prove some equivalence to show that AM is in NP, if you did not change your definition for a target generator or leakage resilience, then it would be the same as proving that AM being in NP to the SAT is equivalent to AM being in NP. Do you follow?
So not necessarily. So one thing here is the computability for the targeted generator, right? So in the case of a mild de-randomization, say in sigma 2p, this targeted generator is computable in sigma 2p, right? So there's the classes match, right? So if you're placing AM in sigma 2p, you get a generator in sigma 2p, right? And what's hard is, if AM is in NP, do we get a generator computable in NP? Right? We do get one for sigma 2p by this result. Yeah.
Okay, thank you.
So yeah, thanks for the talk. So I had a general question about mild de-randomization. So when we talk about de-randomization with respect to time, we know that it's kind of equivalent to circuit lower bounds. You get some sort of circuit lower bounds just from de-randomizing PIT. Is such a thing true for mild de-randomization? Is there something interesting in this direction?
Yeah, so there's this result, IKW in Pagliazzo, Cabinets in Wigderson. So if you can get a slightly better simulation for BPP than it being in NXP, so say sub-exponential time, then you get the circuit lower bound in exp is not in p/poly, so it doesn't have polynomial size circuits. And essentially, same thing holds one level up for AM and sigma 2.
So what would you assume then? So AM is in n sub x to the SAT or something.
Yeah, exactly.
And you would get as a result of it.
So you get the lower bound in exp with a satisfiability oracle is not in NP/poly. Yeah.
Okay, thanks.
Any more questions?
Hello, thank you for the talk. My question is probably basic, but like, does it make sense to ask this question for Merlin Arthur protocols?
Yeah, it does. One thing is that because Merlin goes first, right? All that's left after the non-determinism is a randomized computation, right? So in that case, if you can de-randomize BPP and even a mild de-randomization, like to be technical, it needs to be the promise version, which I kind of shoved under the rug here. You get a de-randomization for MA, right? So in a sense, de-randomizing MA is easier than de-randomizing BPP because a mild de-randomization for BPP is enough.
Thank you.
Okay, so let's thank the speaker again.
Thank you.
Nice talk.
Thank you.
Hello.
You have to long press. Long press, apparently.
Okay, so welcome back to this post-lunch session. We have two talks in this session. And the first talk will be given by Nikhil Mande. He will tell us about randomized and quantum communication complexity of equality.
Thanks, Meena. And thanks everyone for coming. Yeah, I'll be talking about randomized and quantum communication complexities of equality with small error. This is joint work with Olivier Lalonde, who's a master's student at Montreal, and Ronald de Wolf, who was my postdoc host before I moved to the University of Liverpool. So a few things. I apologize in advance if you're looking for some quantum stuff. I will skim over quantum details because a lot of the proof techniques that we use for our randomized results, similar ideas can be used for quantum results. And yeah, defining the quantum setup formally would be a bit painful. Also, I realized this is after lunch, a heavy lunch, nice biryani and stuff. And also that there's no parallel track B session. So I've tried to keep it a bit accessible. And if nothing, please go back with the primer on communication complexity. Yeah. You can bunk your first lesson in communication complexity if you plan on taking a course. Yeah, don't tell the instructor I said that. Right. So or apologies to the instructors. Yeah. Right. So here's what I'm going to do. The outline is I'll just tell you about the model of communication complexity. I'll define this equality function that appears in the title, which is arguably the most fundamental problem in communication complexity. You see it in the first lesson if you take a communication complexity course. And then I'll tell you about the results. And if I have time, I'll actually prove one result completely. Good. So communication complexity was okay. It was introduced. It was introduced by Yao in the late 70s. Yeah, if there's important stuff covered by preparing live stream, I'll just speak it out. Yeah, so it was introduced by Yao in the late 70s, and here's the setup. Communication complexity was touched upon in an earlier session today, but it's a slightly different setup here. So here there's two parties, let's say Alice and Bob, and they wish to compute a Boolean function f, but the input is distributed amongst them. So Alice has an n-bit string, Bob has an n-bit string. They each know their own string, but not each other's. And in this setting, we assume that Alice and Bob individually are computationally unbounded. Yeah, so they have access to supercomputers, they can solve the halting problem, whatnot. Yeah. But the resource that we're trying to constrain here is the amount of communication between them. So how do they evaluate this function? They do so by executing what we call a communication protocol, which I'm going to describe via figure here. So Alice starts with an input X that Bob doesn't know. Bob starts with an input Y that he knows, but Alice doesn't know. And both of them know this function. Yeah. So they agree upon this protocol in advance. And let's say the protocol dictates that Alice starts by sending a message to Bob. So this message M1 is a function of F and X. Yeah. So M1 could be a bit, it could be a sequence of bits. Now Bob, the protocol will then dictate that Bob, on responding M1, replies with a message M2. Now this message M2 could be a function of Y, M1, and the function F. Okay. And they carry on like this until the protocol tells them to stop, at which point they jointly output an answer pi of xy. And typically the correctness requirement would be that pi of xy is equal to f of xy for all x comma y. Okay. I'll come to the precise correctness requirement later, and the precise cost measures. But informally, for now, the cost that we're trying to minimize is the number of bits communicated across all of these messages. Worst case overall inputs xy. Okay. Okay. this is a motivation slide. I think I can go through it anyway, even while it's being fixed. So I'm not going to preach to you. I'm not going to invent some of my own motivation why communication